Okay, we are live now. Okay, so thank you for coming here at this workshop, and thanks for the physics department for hosting us, and for the John Templeton Foundation to give us a grant to do this. So we're going to do something a little bit different than usual. One of the problems in the foundations of physics is that essentially every person, every group has their own approach that work on a particular subsystem of the foundations, and with a little connection from the other. So if you go to a Foundations of Physics conference, you basically have just a bunch of talks that are disconnected, and the interesting part actually happens during the discussions. And so I thought, why don't we just essentially skip the talk and just have the discussions and try to find the pieces that are, so that we have these translations between what we are doing, and I try to understand how all these pieces fit, because my interest in the ascension of the physics process is really to find these pieces that have to be there in all of the physical theory, so that we can have a more cohesive view of what is it that we need to do. So without much further ado, I'll just start. I'll give sort of a 10-minute introduction to what is it that we aim to do. And then we'll have a more in-depth discussion with possibly things that are interesting to other people. Okay, so the whole idea is that we're trying to develop a general theory for statistical sample as part of our Assumptions of Physics program. Our Assumptions of Physics program, and of course, this does not work.
Re-click this slide.
There we go. So just to give you an idea, the main goal of the program is to find a minimal set of assumptions from which we can derive the law. We want to be able to say something that if we assume infinitesimal reducibility, we get the classical state. So if we have a system and the system is made of parts, we can study the whole system, or we can study all the infinitesimal parts. And under that assumption is the classical state emerges. And instead, we want to say that irreducibility gives us the quantum state. If you have an electron, you can't take a red marker and make a little dot on the electron to understand what that part of the electron is doing. You can study only the electron as a whole. And the idea is the quantum state is that. It's the fact that you have inaccessible information of the system. To be able to do that precisely, we need to do it also at the mathematical level. We need to rederive all the mathematical structure from physical assumptions, so that we know when the mathematical structure can be assumed and can be valid. So we want to be able to say something like science is evidence-based. Therefore, a scientific theory must be characterized by experimentally verifiable statements that have a test, and the test succeeds infinite time in following if the statement is true. And then we can show that from that, we get the topologies of n-sigma algebra. So those mathematical structures that are a foundation of differential geometry and probability theory come from the fact that we have experimental evidence, so that we know when those things are valid. So this is more or less what we want to do. We have two approaches that we use to go about this. One is called reverse physics. And the idea is to break physics into different conditions and study their logical relationship, which is the type of things that people do in Foundation of Math. Foundation of Math, you have the axiom of choice, and you prove that it's equivalent to the Zorn's lemma. And now you know that those two things have the same expressive power. And so we want to do the same thing within physics. We want to be able to say that this condition of the Schrödinger equation, that the evolution of quantum mechanics follow the Schrödinger equation, is equivalent to the fact that the information theory is the von Neumann entropy is preserved. And so you can assume one and prove the other, and so on. So this is the type of thing that we want to understand, so that we have a better sense when we want to reconstruct a physical theory, what are the main ingredients that you have to put in. And for classical mechanics, we already have done extensive work. And you basically have a graph that looks like the type of graphs that you would have in, again, Foundation of Mathematics with different conditions. This IR is this infinitesimal reducibility that I talked about before. IND is independence of degrees of freedom. These two together, they give you CST, which is the classical state. dr is determinant of reversibility, and that together with a classical state give you Hamiltonian mechanics, HM. And every element in that graph is actually an equivalence class of different conditions, much like these two conditions of the Schrödinger equation of information preservation are the same. And so the idea is really to break up all these things. And the goal is really to find then a base theory for all of physics, which basically is the set of conditions that must be true in all the physical fields. So for example, in this condition, we say that if you have two events that are mutually exclusive in the sense that the probability of getting one from the other is 0, then we also have their mutually exclusive in the entropy, because when you mix them, the entropy is the Shannon entropy. And this is something that, with some argument, you can see that is something that has to be true, because otherwise you would have two different notions of mutual exclusivity that wouldn't mesh with each other. And so the idea is to find all these conditions that are the ones that are that we have to assume to be true in all physical theory, and that basically is your base theory. And then on top of it, all the classical mechanics, quantum mechanics, and all the other physical theory become what specific theories within that context. And that base theory is not a theory of everything. Theory of everything is one particular theory, and also a theory of everything has to obey the axioms and the conditions that are there in the base theory. And since reverse physics only works from the theories that we have, we can't really do this work with just in the context of reverse physics. So we have another approach that we call physical mathematics. And the idea is to start from mathematical axiom with a clear physical justification. So we basically say the statistical mixture of two ensembles is an ensemble, which is something that any physicist or engineer will take it to be true. And then we have a formal definition, and which is something that a mathematician would like. But then we also have a justification to show that the formal definition follows from the intuitive requirement. So now we are much more grounded, because we do have the mathematical structure, but we know exactly what it represents. And we know that if we are representing that, we have this mathematical structure. So everything that follows, all the theorems and the proofs can be reread as an argument. And these, I think, are really the pieces that we are missing in the foundations of physics, where people found with interpretations that the problem is that a single mathematical structure can have million interpretations, and we need to start from the physics and rederive them. So that's the idea. And in the context of this workshop, the thing that we're interested in is the fact is this starting point, the fact that the scientific laws describe relationships that can always be experimentally reproduced, and therefore scientific laws are relationship between ensembles. So a preparation will give us an ensemble, a process will be something that takes an ensemble and gives us another ensemble, and a measurement is also something that takes a physical ensemble and gives us an ensemble of the output of our measurement. And the ensemble has to be, is basically thought as a preparation procedure that gives us a possible stream of outputs. And so, again, the point is that this has to be the case, because if science is repeatable, those are the things, are the building blocks that we need. And so what we want to have is understand what are the minimal set of axioms that we have to put on a theory to have a well-specified space of ensembles. Without that, we can't do science. So we need this. There are 4 pieces that we have identified that are a source of, let's say, requirement. The first one is what I said before, experimental verifiability, the idea that we have a verifiable statement, and that will give us a topology of a sigma algebra. Then the second one is what I also said before, the fact that we have statistical mixing, the fact that if we have to ensemble A and B, we can make a convex combination with some kind of coefficient, and so we get a convex structure. Then we have the idea that these ensembles have variability inside, because you don't always prepare the same thing. And that variability is captured by the entropy. And the entropy is the thing that is responsible for geometric structure in physics. And then the part that I still don't know exactly how it works is the fact that ensembles have to be equilibria, they basically, our ensemble have to exist for at least, our physical system have to exist for a finite time, because we need to be able to prepare the measurement and talk about them. And therefore, if they're equilibria, there have to be symmetries of processes. And the insight should be that these symmetries are what give us the Lie algebra, the Poisson structure, and that's what we want to be able to talk about. So in all this context, there is of course some type of probability that needs to fit in, and that's why Hert and Alessio are here. We want to generalize the idea of probability calculus so that we have a derivative and integrals, and in that context we might need non-additive measures, and that's why Susanna is here. And then there is this part about Lie algebras and Poisson structure and how to generalize that, and I have no idea how to do it, and that's why Marcel is here. So let's go in some of these questions. So now I'll basically tell you all the things that I don't know how to do. What is the relationship between probability as used in physics and is used in a more general sense? Because probability can be applied as an inference to non-repeatable effect like political election, and it's definitely not what we're doing in physics. So the scope of probability theory should be bigger. What is the piece that we are interested in physics? Probability can be defined on spaces that lack physical structures. For example, we need a symplectic structure in classical mechanics to define phase space and Hamiltonian mechanics, but you don't need the symplectic structure to define the probability distributions. So clearly, there is more requirement in physics than in probability. So it's obvious that probability is not going to capture all of physics, and that's fine. I just want to understand what it was. And a conjecture here, if probability are defined in terms of bets, which is what you guys like to do, and we are applying those bets to physical systems, is the physical knowledge of the state space exactly the knowledge of all the sure bets? Because you know what's going to be the evolution, you know the constraint of the physical system, and therefore you're not going to bet on something that does not follow the equational state of your system. And given that the entropy plays a fundamental role in characterizing ensemble spaces, is that knowledge equivalent to the entropic structure? No idea, up for discussion. And another general question is, can we use non-additive measure to characterize statistical ensembles when mutual exclusivity cannot be assumed? So the idea is that in Kolmogorov probability, additivity is equivalent to assuming that all elements of the sample space are mutually exclusive. So they're mutually exclusive, therefore the frequency of one plus the frequency of the other is going to be the frequency of the whole event. In classical mechanics, the additivity of the Liouville measure, the count of states, is equivalent, is additive, because we're assuming the states are mutually exclusive. So it's the same condition. Additivity gives you the same condition in both. And so subjective measures may be used to describe the case where mutual exclusivity is lost, because there is some overlap between these events. And therefore, when you put things together, you have some interaction that you don't want to count things twice. And therefore, your addition is going to, your measures are going to be set up. And so the question is, if this is true, how do we specify that well? And what type of integral and derivative can be used to generalize probability calculus in this case where we have non-mutually exclusive events? No idea. How can we generalize the Lie algebraic structure for classical and quantum mechanics? So in classical mechanics, we have our Poisson brackets. In quantum mechanics, we have our commutators. And they essentially represent how things behave in during generated transformation. And so what is it that these things are describing, and how do we generalize them? So what is the right structure that we should put on space of ensembles so that the standard ones are recovered in the classical and quantum case? Should we understand the elements of the structure as observables, like we typically do, and observables in the context are just linear functions of the state space? Or should we understand them as generators, that is, a derivative of one parameter groups? These two things are different. Are they exactly, like they're different definitionally? Are they exactly the same? Are they not the same? I have a suspicion that the generators are more powerful, that tell us more things. No idea. I hope that Marcel can tell me something about that. And what is the right product to generalize the Poisson structure? So if you don't know, there is a structure called the Lie algebra, and then there is a structure Poisson, that is called a Poisson structure, and a Poisson structure is a Lie algebra that behaves well with a product. And it is not clear to me what that product should be, because in classical mechanics and quantum mechanics, the two products are different. There is no like they're so different that I don't even know what they're doing and what's the right way to generalize. And so this is a big piece that I don't know how to do to be able to impose this fourth structure. And I think it also needs to tell us something about how our ensembles and probability distribution work as well. And which leads to this one, to the last, how does all this work in infinite dimensional spaces and field theory? Because these are the typical thing that gets swept under the rug. How do we put probability spaces in field theory as something that I have no idea how to do? So what is the right probability space for function spaces? And are there constraints on the function space such that, oh no, the function space has to have this property, I don't know, the Haney-Borel property. If you don't have the Haney-Borel property, you can't put function spaces, probability distribution of that. I have no idea what you need. Then the linear entropic structure does not seem enough to characterize infinite dimensional space, meaning that if I have a Schwartz space in one dimension and a Schwartz space in n dimension, these are isomorphisms as locally convex topological vector space with an inner product. And if we take the Schwartz space to be the state of, say, quantum states with n degrees of freedom, we would be saying that 1 degree of freedom is exactly the same that n degree of freedom. So, you're doing information theory in 1 degree of freedom. It's the same as doing n degree of freedom. You have the state of a billion particles. You can encode them in the state of one particle, which of course makes no sense. And so the fact that these two structures are isomorphic as this structure, then it means that this structure doesn't have enough information to tell us what the physics is about. But it seems that the Lie algebra is able to distinguish, because if we get the generator of position and momentum and we look at their commutator relationship, the number of independent generators depends on the number of degrees of freedom. And since a linear operation cannot change the number of independent generators, then it means that a linear transformation cannot make an isomorphism between one particle and one billion particles. So that there seems to be a sense where these Lie algebraic structure that I don't know how to extend are actually necessary to be able to talk about things properly. And that's one of the open questions and the mystery. And again, is there a way to understand the Lie algebra as properties of the probability calculus and relate them to rules of inference? So if they represent transformations, then on the probability side, it would be, again, processes on these probability distributions, what they're doing in certain contexts. And so that's basically the idea. So these are all my questions. I don't think we're going to answer them all in these 2 days, but
just in the morning.
Just in the morning. But I hope there are going to be some of them that are interesting enough to like an intersection of you guys, so that then we can say, okay, let's try exploring that and so on. So that's basically it for the overview. And now I'm going to go through the details. And as I said, you feel free to stop me if there is something that you guys don't understand, so that we can have a productive discussion. So let's start from the basic. Hopefully this will go fast. So these are concrete examples. So in the classical space, we have a discrete space with just a bunch of points, countably many, and we have probability distribution of that. Hopefully that's not controversial. For the classical continuums, I will require that we have a phase space so that we have a symplectic manifold. So it's not just a probability space, it's a particular one. And I want the distributions to be integrable, but I also want them to be absolutely continuous with respect to the volume form, such that we can write a probability density, and the probability density should also give us an entropy value.
Can I ask just a fundamental question here? I mean, you touched on a couple of times. I mean, is this all real space? Because, what's the base field? Are you locked into R?
No, as you see, so the way that it's set up, and you will see, I will talk about ensembles without knowing what they're ensembles of. Right, so it's gonna be clear once I start showing the axiom. These are just examples that the axiom that we're gonna set up have to allow. Because if I have a set of axioms that don't allow me to do classical discrete spaces, classical mechanics, and quantum mechanics, I have something that doesn't work. Okay, so this is the classical one. And the quantum one, we're going to assume that we have some type of projective Hilbert space, and the ensemble space is given by all the positive semi-definite condition self-adjoint operator with trace 1, which is the space of density matrices. And if you don't know what that is, then just ignore it. It's just a space. There are some caveats here that even these specifications are not quite correct, because we will need to have an entropy, and not all the probability distributions have an entropy well-defined. So even in the classical discrete space, you can find a set of the probability that sums to 1, and the entropy diverges. Another problem is that typically on these spaces, you're going to put a topology which is the total variation topology. The entropy is not continuous in that topology. So there are all these caveats that really tell you that we don't have the right spaces because they haven't been seen from all the different sides. Part of the goal here is to find exactly what these missing pieces are, and I'll highlight them as we go on. But morally, these are the 3 things that we're going to be talking about in a more generalized sense. Okay, so the first 2 axioms are the fact that we have a topology that is T0 in second countable, and the fact that it's T0 in second countable is a necessity because we can only go through countably many verifiable statements. So if the space is not generated by countably many verifiable statements, we have a space that is not explorable by us. So it's too big, doesn't matter. And it's T0 because the cases have to be separated by a verifiable statement. There has to be a verifiable statement that says, given 2, if this is true, then this is one is the right one and not the other one. And so the space is actually T0. It's actually a sober space, but don't care, T0. And then the other axiom is the fact that we need to be able to make mixtures. We need to be able to take 2 ensembles and mix them, and we have another statistical ensemble. So hopefully these 2 are not controversial. And these 2 lead to the notion of a topological convex space, because the addition has to be continuous in the topology. And the modern analysis based on the topological vector spaces, but there is really no work on topological convex spaces. And a lot of the stuff that we have is to understand how this works and how they relate to the other, and do we have enough information to prove there are topological convex spaces always embedded in a topological vector space continuously? And if not, is there interesting physics to be lost if we consider topological vector space? The algebraic structure only defines finite convex combination, and it is the topology that allows us to define infinite convex combination in terms of the limits of convergent sequences. This is exactly what people do in topological vector spaces. And we still don't know how to define a notion of convex integral, because I don't have a standard way to define convergence in a topological convex space. Topological vector space, you can use the difference to create your Cauchy sequences. Here, I don't have a difference because I can only add the 2 things. So I don't know what is the right criteria of convergence. Maybe there is one, maybe there isn't. I have no idea, but this is an open problem.
Well, so I mean, why can't we use, distance between probability measures? I mean, you don't have to measure distance between points. You can measure distance between probability distributions.
Because there are multiple ways to define the distance. There is not a single way.
There are multiple norms, and most of them are equivalent under certain conditions. I mean, I don't understand why it is a problem.
Because I need to know what I can justify physically. I can't just say I have a norm. I have to say that is the right norm to generate the topology because it's connected to experimental verification and so on. I'm not allowed to assume anything until I have like a page of justification that tells me why I have to assume that. That's the game.
I was just wondering, every convex space generates a very simple linear space, right?
No, so not all convex spaces defined like that embed in a linear space.
Are you sure? Yeah, that is a given. Yeah,
They did not.
they did not. Okay.
In fact, what we'll see is that the entropy forces us to embed in a linear space. Right now, with these two axioms, you don't know.
Okay.
Can I ask you something? Why? Can you go back to the mixed space assumption that you have?
If you want, in the book, there is a whole justification where I go through all these properties and show you why they make sense.
No, I was just wondering, compared to a standard or mixed space axiom, what is actually that doesn't allow you to embed it in a vector space? Because these you can always do it, no? I mean, so there is some assumption that probably you are.
Yes, so the assumption is cancellativity of the space. Do I have it?
Somewhere, no.
I don't know if I am. I don't have the definition here. So the assumption is the fact. Let's see if this works while I write on the board. So if you have PA plus P bar B, bar is one math, and then you have lambda A plus lambda bar C. So if you have this condition, then B and C are the same.
Yeah.
Mm-hmm.
And this is the cancellative property. Did I get it right?
P and lambda have to be the same. Well,
Yes.
otherwise it would be somewhere
Yeah,
along the line.
Thank you. There it is. So if you basically say PA plus P bar B is equal to PA plus P bar C, then these two things have to be the same. That's known as the cancellative property, as in an if and only if. So a convex space embeds in a vector space if and only if this property is true.
Why are you not assuming that? So you say that you don't want to assume that, no? Or are you?
I don't assume it because I don't know physically why I justify it, but then the entropy shows that this is
Yeah, exactly. No, because that you need that for that. Yeah.
Yeah. So the space would kind of look like this. Like this would be a convex space that is non-cancellative. So you mix these two and you go on this line, you mix in these two and you go in this line, right? But then when you get here, you don't know how to go back. And for sometimes I thought, oh, this might be new physics. And then I proved that, oh no, it's not. So this is kind of the style we want to go through all these little things and make sure that we have a minimal set of assumption that we can get. So there is no point of assuming also, because now I know that the entropy forces it. So that it comes from there.
I think, Marcel and Susanna, do you see the blackboard writing backwards?
No.
Is it, I see it backwards up there.
Yeah, it's mirror imaged. That's
Do
fine.
you see,
Yeah, you might.
you see a mirror image?
I don't quite see what's been written on the blackboard,
That's a different problem.
but I've been listening.
It's still
Yeah, it's not quite visible, but listening to you is fine for now.
But it's mirrored, right? You need to do the.
I think it's just mirrored on us, right? If usually you mirror locally, not what you send. I think it's fine.
Is it mirrored for you?
Zoom, you have to mirror. Yeah, show it.
So
Just type B.
how does that?
B.
But you-
Mirror. There you go. Okay, can you read that?
Is it mirrored?
We can see that you're writing from left to right, so we probably could see it correctly.
Okay, there you are. So you see it.
It's
from left-
it's too small because the talk is
There's the-
large. Yeah, but that's fine.
You're right.
Yeah, it's a reverse, like usually it's reverse for you.
Yeah, for all.
Okay, but yeah, this is exactly the type we want to do. We want to go through all these things little by little and get them right. So some terminology that I might intuitively say. So if E is a PI-AI, then E is a mixture. These PI are also called mixing coefficient, and these are components of these mixtures. The P bar is 1 minus P because I don't want to write 1 minus P all the time. A and B, if I can write that A equal PC plus P bar D and B equal lambda C plus lambda bar E, then we say that A and B have a common component and C is a common component. Okay, so there are pieces of the ensemble that is the same, and A and B are separate with this, kind of pi-looking symbols if they don't have a common component. And intuitively means that they're kind of like on separate faces, on opposite faces of the convex set. More terminology, an extreme point, hopefully everybody knows what it is. It's one that can only be expressed as a trivial mixture. So if E is a mixture of something, then the two things that you're missing is the thing itself. And then a set is convex if it's closed under finite convex combination, that is, it contains all its mixture. It's sigma convex, it is closed under infinite convex combination, so it contains all the infinite mixture, and it's closed and convex if it's convex and topologically closed, that is, it contains all the mixtures and all the limits. And these two things are not the same. Then it's componential if it contains all the components of its elements. And it's facial if it's both componential and convex. And these sort of recovers a lot of things that you would have in standard convex geometry. So these are the phases.
Can I ask just a clarifying question?
Yeah.
You're using two types of operations here. I tend to call them addition and multiplication. Do you have axiomatic definitions of these operators?
I don't have
Not
addition
sure
and
you
multiplication. I only know how to make. I only know how to make this. I know how to take two elements, get a number from 0 to 1, and give you something. The fact that I'm writing it as a PA plus P bar, that's just
I see. Yeah.
Notation.
Yeah.
It's just notation. But the thing that I've defined is just this, and I know that this is continuous. Right. So if you go into the literature, people would write something like C lambda of X and Y, right? So they would use this notation so that it's more clear. But if you start looking this rotation, I think you lost like 99% of the physicists that would be interested in this because it's just not you don't understand what's going on. So it's much easier to just use this notation. But in the back of your mind, you know that that's the definition that you have.
But it's a good question because I hadn't realized that was what you're doing. You were doing, yeah.
Yeah, usually another notation is with the O plus, no,
Yeah.
sometimes they use it. Just,
Yeah, this can lead to a lot of confusion and misinterpretation, to be honest with you. Because for most of us that come from a mathematical background,
I understand it.
very well defined multiplication and their inverses and all that business. So for instance, here you're saying on your top equation, you can't really, there is no association, you can move elements.
It's stuff that you will recover later. Because what happens at the end is that we have enough structure to say that these things are gonna embed in a vector space. So we're gonna recover those things. So having a notation that then afterwards give you the same
Change it. Yeah.
And again, if I go to a physicist and I write,
Okay, so how do you define? Because you were saying you go from 0, 1, you go from this compact domain.
Yes.
So how do you define P and P bar?
This is P, and P bar is just 1 minus that.
But what's 1 minus that? What's 1 minus that? Because
This is a real number.
okay, so now all of a sudden you're introducing the inverse additive operator minus.
On this is the real number. I can do all the things that I do with real numbers.
I mean, you see where I'm coming from, right?
Yeah.
Addition and subtraction are inverse operations.
Right, so we have those things here. In fact, this, where is it? The fact that you can flip around, like this commutativity that you have here, right, assumes exactly that you can take a p and make it a one minus p, because that's exactly what's going to happen here. You're going to switch the order of these two and put a one minus here. So it's not, so that problem does not change whether I'm using the plastic annotation or I'm using the C lambda as annotation. It's the same thing. The fact that I'm using plastic is just a coat of paint to make it more understandable. Okay.
It's good to be aware.
Yeah, it's good to be aware.
Well, so if you want, do you have some assumptions on like why P is the probability is a real value between 0 and 1? There is something hidden
It's
inside
not a
of it.
probability.
Very good. It's not a probability. Very good. Yes.
It's just a number.
A mixing
A mixing
coefficient.
coefficient.
Yeah.
It's the mixing coefficient.
Yes.
And okay, good. The fact that you already know that it's not a probability makes me happy. Yeah, I see it basically as a parameter of the preparation more than okay, so we have all these things: the convex, sigma convex, closed, componential, and facial. And okay, so limitation of probability of this structure effectively. Of course, this structure is not enough for physics because the space of probability measured over R square is the same regardless of what we've seen. But the thing that is more interesting to me is that this structure can tell us if the extreme points are mutually exclusive. So suppose that you have this triangle, which represents the space, the simplex of probability distribution over three things, right? Then the edges, the vertices, are mutually exclusive events. Now you can say I take a smaller triangle inside because I'm representing a space of preparations that are always noisy, right? So all the other things are things that I cannot prepare, so they don't exist for me. Now this, in terms of the convex space and the topology, looks exactly the same as the bigger one. But it's not. And I know that it's not because the vertices are not going to represent mutually exclusive preparations. And same things, if I'm using expectations, right, I would have the same structure. I have the same linear structure and I have the same linear functionals and so on. So the point is that the P's that I have in preparations and the expectations are not enough to recover mutual exclusivity, and therefore they're not enough to recover the actual probabilities. I need something else to tell me when things are mutually exclusive. And that is the entropy. And this is the action that I have on the entropy so far. We have a function that takes for HC ensembles, gives us a number. The number represents the variability of the instances within the ensemble. It tells us how varied the elements of the ensembles are, but we're not allowed to talk about the elements of the ensembles. But we are allowed to talk about its to characterize its variability. The entropy has to be continuous because small ensemble changes have to lead to small variability changes. It has to be strictly concave because the average variability cannot decrease during mixing. If I take two things and I mix them together statistically, the average variability can go up or stay the same. It can't go down. Then I have an upper variability bound that it's maximized when the events are mutually exclusive. If I have two sources that are mutually exclusive and I put them together, that's the maximum variability that I can have to increase. If I mix two things that have elements in common, then the amount of variability decreases less than that. And then the third thing is that statistical mixing preserves mutual exclusivity. So if A and B and A and C are mutually exclusive, if I mix B and C, then A is going to be mutually exclusive from B and C. And conversely, if A is statistically, it's a mutually exclusive from a mixture of B and C, they have no elements in common, then of course it's going to be mutually exclusive with B and C as well. So this may not be all the property that we need, and the problem here that this is the only axiom that I have on what happens between 3 points, and you only get information when they're mutually exclusive. So if you have spaces where things are not mutually exclusive, You have no idea what happens to 3 points. But in the case where you do have minimal specificity, that actually is already enough to do a lot of things. And so that's what I'm gonna through. Is it clear enough what this thing
Can I
is?
say something? That function, the IT bar P.
Yeah.
Does this depend on the dimension? I remember, no, it's not.
No, and the next slide is that you find that this has to be the Shannon entropy.
Okay.
This is the interesting thing is that we leave the upper bound unknown, but we don't know what it is, but we know that there has to be one. And then what you're able to prove in complete generality is that that upper bound is the Shannon entropy. And this is the trick that we use. Like we don't know what the points are, but we know at each level when we're mixing things what happens. And so these differences are the things that we can always talk about, and they're always the same in classical spaces and quantum spaces. And since these axioms have a justification, we think that they are valid for any physical
To find the motivation for the last property, the mixture preserves orthogonality, I can look at the website.
Yeah. So this is all in the book. In the book, if you go in the chapter of ensemble spaces, after each axiom, there is like a page of justification that tells you, suppose you have 2 preparations, and then you have something, and it tells you like operationally why this thing should. And yeah, if you go and nitpick and find problems, that's exactly what we have to do. Is we have to bang on these things until everybody says, oh yes, this is trivial, and it has to be. Okay. Okay, so we recovered that this is the Shannon entropy, and we recover a lot of things from the entropy. So we find that the entropy, because it has to be continuous, forces the topology to be Hausdorff. I have a sense that it might force it to be metrizable, because in topological vector space, once you have a second countable T0 or T1, T0 even, topology, then it's automatically metrizable. So this is one of those things that, does this hold in topological convex spaces? I don't know, right? If it did, then we already know that would be metrizable, just by that. The entropy forces the space to be conservative. And so affine combination, if they exist, they are unique. And that gives you the fact that they embed in vector space. Here we should probably simplify. And now we can say that a set is affine if it's closed under affine combinations. And it's closed and affine if it's affine and topologically closed. And now we can define affine independence. We can define a sort of an affine basis and then the dimensionality of those sets. Which is all very cool because we haven't really put anything in these axioms. That's the thing that it says. We think that we can prove that every finite dimensional affine set embeds continuously in a topological vector space, and that it has to be bounded, that the entropy bounds things. In infinite dimensional, we do not know whether we embed continuously in a topological vector space. I think I found a Strawman counterable example, but I still have to go through it and make sure that it actually exists. But we are sure that they're not going to be bound. So whatever that means, we don't have. Then we can define statistical quantities as affine functionals. So you have a function that takes an element of the ensemble space and gives you an element of another convex space in a way that preserves convex combinations. And of course, the one that we're more interested in are the one that maps to real values, and we call real values, and we call them statistical quantities. And of course, the space of statistical quantity is the topological dual. And one of the things that I don't know is how to characterize the statistical quantities that are expectation of random variables and observables in classical and quantum mechanics, and the ones that are not. I still don't know how to do it. And we can say that an ensemble is quantifiable if there is a family of statistical quantity that generate the topology. And the topology, since it has to be Hausdorff, it will separate points. And therefore, the suspicion is an ensemble space embeds continuously in a locally convex topological vector space if and only if it is a quantifiable space. If I were able to show that from the entropy or from something else that the space is quantifiable, then we can say, oh, then we can do derivatives, we can do everything. I don't know that yet.
So this FI, is that a finite countable list or what is this? Or is it?
So you say that it's a family, and if the family generates the topology, since the topology is countable, then you're going to be able to find a countable subfamily that still generates the topology. And since the topology has to be Hausdorff because it needs to generate the entropy in which the entropy is the topology in which the entropy is continuous, then the topology has to be Hausdorff, and therefore they have to separate parts.
Sorry, what do you mean by generating here? Is it because you assume from the beginning that it is continuous? This statistical quantity?
Yes, they're continuous affine maps, yes.
And so by generating would then mean that they're all that there's the smallest topology that makes all of these continuous, right?
Yes. Okay. You take the inverse image of open sets, yeah.
Yes, so about to recover the expectation in probability and quantum mechanics, but I guess you need to assume something about what A and B are. No, you cannot do it in general, no?
Right. So if this is quantum mechanics, this A and B would be density operators.
Exactly, and then I guess probably you can do it up to isomorphism. No, I guess. So you can always, I don't know, whatever expectation you define as, you can always probably map back to the density matrices.
Yeah.
So I guess, yes, I think you should be able to do that. So once you choose the objects,
Yeah, this is true in classical and quantum mechanics, this is true.
Okay.
Yeah.
I see, okay.
So in classical and quantum mechanics, you have quantifiable spaces. Yes. And in fact, you can then define, if you don't have, so since these are locally convex topological vector spaces, these are exactly the spaces that you need, for example, to define derivatives. Because if you don't have enough linear functional to go and look at the space, you can define a derivative, but you don't know how to use the derivative to describe variations around. And so yeah, this is something that in some sense, I kind of feel that we need to have, but I don't know right now that we have to have it, right? And again, since we're going from the bottom up, I want to understand if there is a physical requirement that tells you, oh, you must have it. Okay, and then with the entropy, you can do a bunch of things. You can, if you have A and B as two ensembles, you can say, how much does the entropy go up when I mix them? And I define this quantity S that I call mixing entropy. And it's a pseudo distance because it obeys all the axiom of a distance except a triangle inequality. And you recover the classical and quantum Jensen-Shannon divergence, if you guys know what it is. And the open balls generate the total variation topology. But that topology does not guarantee the entropy to be continuous in infinite dimensional spaces, which is completely bizarre. But anyway, the point is that the topology of this thing generates should be interesting. And of course, I have no idea how to study it in general, but it exists. And then what you also can do, since the entropy is strictly concave, if you also assume that it's differentiable with respect to the space of mixing coefficient, you can define an Hessian. Therefore, the negation of that Hessian is going to be a positive definite function of two variation. And so it's kind of like a metric tensor. And in fact, it recovers the Fisher-Rao metric and the quantum Becky-M metrics in the classical and quantum case. We're not going to do information geometry, but the point is that this is the type of things that we want to have. We want to have links to as many things with as little work as possible. So here already we connect to information geometry very quickly. I need more. Do we have? Oh, sorry.
Yeah.
Okay. Okay, so before we said the two ensembles are separate if you don't have a common component. And here we said that two ensembles are orthogonal if they saturate the entropy. Now, these are two ways to define how much overlap there is between ensembles. And they actually coincide in classical ensembles, which basically is just disjoint support. And in quantum mechanics, they're different. And this is one of the things that makes quantum mechanics strange, because there are two different definitions that in classical mechanics give you the same thing, but they are different in quantum mechanics. So in quantum mechanics, A and B here, psi A and psi B, are orthogonal to each other. So they are also separate. And A and C are separate because they don't have any common components. They are both pure states, but they're not orthogonal. And the difference between those definition already gives you a lot of sense of why classical and quantum mechanics are different. It allows you to characterize things. And just to remind you, orthogonality is a mutual exclusivity. And so, disjoint support means mutual exclusivity in classical mechanics and so on. So it sort of conceptually and mathematically, things map very well. This is another thing that Herter sort of said before. In general, the mixture of preparation and the probability of outcomes do not coincide. In quantum mechanics, you can see if you ask what is the probability of measuring Z plus, if you have an equal mixture of X plus and Z plus, this is not 1/2. It's going to be more. And so they coincide only if the ensembles are mutually exclusive. So entropy is necessary to transform mixture coefficient and expectation value into probability of outcomes. This is like a flaw that you see in a lot of work that is done in some type of generalized probability theory, that they just use the convex structure to get the probability out. You don't have enough information to do that.
I mean, the probability of the measurement.
Yeah.
The probability.
Because as Hertz saying, these two things are different. These are defined only when things are orthogonal, and they are orthogonal because they're mutually exclusive, because you have the entries, and it's the same thing. If I told you what things are mutually exclusive, then you can recover the entropy. Like those things are basically the same structure. So this thing that you can do with orthogonality and separateness, you can create subspaces. Because separateness and orthogonality are symmetric and irreflexive relationship. And if you have a symmetric and irreflexive relationship, then you can define a complement. So, all ensembles that are orthogonal to other elements of the original set. And then you do it twice, and that's a subspace. So if you have a set that it's orthogonal to its orthogonal complement, it's a complement of the complement, then it's a subspace. And then you can define this lattice of both separate or orthogonal subspaces. And again, because these two things are different in quantum mechanics or in other physical theory, they are different lattices, and they coincide when you are in a classical space. So for example, this is a triangle where we cut the top, meaning, we can't prepare those ensembles. We can only prepare the one in the trapezoid. If you take two and you ask, what are the complements, the separate complements, so all the elements that are orthogonal to two and mutually exclusive, then you get the set between B and 3, this side. But if you ask for the separate complement, what are the elements that are separate from 2, you get A and B and B3. And so you get something different. Which gets us to all the order structure that we have now. Yes, sorry.
I was just wondering, is this, because this makes me think of the polar of a cone, right? And the polar of a polar is that thing there is like, for me, when I read it, it's like the set of all linear functionals such that something is positive on those linear functionals, and then you go on with that, and then you get typically the cone back. So this is what I see, but you probably,
I don't know if it's the same thing. Exploring and seeing if it's the same thing would be exactly the thing.
Yeah, and also because this should also be related to like the tensor product in quantum mechanics, because you get that kind of try to first you have some two systems, and then you try to look at some systems, and so this property of having different, let me call it orthogonality or different basically property when you do the dual of the dual. Usually you have that, I would say, this is not the tensor product issue. So in quantum mechanics, so the fact that basically when you do the dual of the dual, you get something that is bigger. Okay.
Okay.
So yeah, so I guess maybe I think that would be
So
it's related. Yeah.
this thing, it's called orthogonality spaces. They appear in Galois structure. They appear in a lot of. It's yet another thing that I rediscovered, and then later I found out, oh, actually, there was somebody in the 70s that already did this. If I only knew what was the name before I developed the whole thing. So I want to see, since Marcel and Susanna are going to talk this morning, I think I want to skip ahead to the things that make more sense to that, so that they have something to respond to, which means I have to skip it.
It's scheduled you until 10:10.
Yeah, exactly. 15 minutes. So, well, okay, let me go through quickly. I need to show you at least this. There are a bunch of lattices, and these are the things where we're going to put the probability measure, right? So we have the topology, we have the sigma algebra, we have the convex sets, the affine sets, these orthogonal subspaces, the affine, the separate subspaces. We have like all these things generate lattices. And most of them are closures, so they are they're closure systems, so they're intersection structures, whatever. You can do a lot of things. And typically, we are going to define our measures here on this sigma algebra. But since they're defined on the hull of the set that you give, they're basically defined essentially on this branch. There might be other relationship between these lattices that I still haven't figured out, but and this morning it occurred to me that there might be the set of closed separate subspaces that might be interesting. Anyway, so one of the things that I want to be able to generalize is how do we represent ensembles as measure, on what set of points and what type of measure. And so we have two things right now. One generalizes the state countive measure, and it's called state capacity. And the other one generalizes the probability measure, and it's called the fraction capacity. And I call them capacity because capacities seem to be a standard word for an additive measure, and it kind of makes sense as a word. So, okay, so for the fraction capacity, it works like this. So suppose that you fix an ensemble E, and you have A, which is all this thing, as a set of ensembles. You're asking what is the biggest fraction of E that can be expressed as a convex combination of the elements of A. So you have E. This is the hull of A. You get a point A, and then you have E as a mixture of A and B is just another element in the whole ensemble space. And you're asking for the highest P. And you can also do it in a classical space. So this is well defined, and it has nice property. It is increasing because if you increase the set, you have more possibility of getting convex combination. It's sub-additive, and it's additive if A and B are orthogonal, and E is inside the hull of the two. So you recover some type of additivity from orthogonality. So again, mutual exclusivity gives you an additivity back. And then it's continuous from below. And so I think it should be sigma sub-additive, which I need just to actually write down the proof, but it should be okay. There is a connection to Choquet theory, if you guys know Choquet theory. So if you have E as a compact convex set of a locally convex topological vector space, and you have X the set of extreme points, then you know that every probability measure defined on E represents an element of E. That is, there exists an element of E such that for every linear functional, the linear function on E is the expectation with regard to that probability measure. Choquet theory tells you that for every E exists a probability measure P on the extreme points that represents E, and that probability is unique if E is a simplex. So you basically have your convex set, you have the extreme points, you put probability measure on outside, and you can represent points inside as an integral of that probability measure. And the connection for us, that if you take all the probability measures that are, that therefore they're additive on the set of extreme points that represent E, the fraction capacity is basically the supremum of all the value of that probability measure on each set. And if you have a simplex, then there is only one element in M, and therefore this is going to be, the fraction capacity is going to be additive because it's just the supremum of a single additive measure. And this is where, okay, we want to generalize this, but the one of, okay, I don't know why I don't have it here, but the point is this is already makes me think of imprecise probability. And I don't know exactly how. Exactly. Oh, there it is. So in the case where extreme points are definable, each subject can be understood as a collection of precise probability. Is there probability in imprecise probability? And can we say that in a classical case, a state corresponds to a single precision probability, when quantum mechanics correspond to an imprecise probability, where the indeterminate is exactly the impossibility of recovering the precise preparation procedure, because all precision give you the same ensemble. You can't know which one is it. You lost information and so on. So I don't know if this makes sense, so and so on. And we also have a state counting analog as a non-additive measure. So if you have an ensemble E, you want to understand what the spread is. And so we ask for a function that has the following property. It's continuous, it's positive, it's increasing, it's subadditive, but it can be, the set additivity can be saturated. We kind of want an idea of volume that represents this ensemble. And the interesting thing is that the entropy, the exponential of the entropy is effectively the only way to do it. And so this recovers what you have in classical mechanics, so that the measure is blah, blah, blah. So we have this state capacity that it's increasing, subadditive, continues from below, and it's additive on orthogonal sets. And so again, we kind of have these two measures now that have to work well together. And so this is the thing that I'd like to have. Is there a non-additive probability calculus hidden inside all these things? So in classical probability calculus, we have a sample space, a set of results, a probability measure. We would have a state count that for each set tells you how many states you have. The probability measure has to be absolutely continuous with respect to the state count, because if you have a set with 0 states, you should have 0 probability of getting that state. And then you get a probability density. This is the radionuclidic derivative. And then you have random variables, and you can recover things with expectations. And so I'd like to have something similar, but with non-additive stuff. Right? It's very easy. I'm really telling you. So you have the fraction capacity for as a generalization of your probability. You have the state count for the state capacity. And then again, you're going to have the property that if you have 0 state, you have 0 probability. So of course, there's going to be some generalization of a random Nikodym derivative, and then we have statistical variables, and then we need some type of integrals such that the expectation, the linear function on that variable is going to be the expectation of the function with the density, or the function with respect to the fraction capacity. So now the question is, what are the integrals and what are the derivative for these things? On a simplex and a classical case, we need to recover the additivity. So it's not the Sugeno integral because it doesn't recover additivity. And Choquet integral does not work in quantum mechanics. And I have an example here, and we could go through it if you guys want. But the point is that it just doesn't work. So we don't know what the integral is. And for the derivative is less clear because, as Susanna will tell you, we don't really have the derivative problem figured out in any capacity in analytic measure. So I don't know, but these are very particular measures. They have a linear space underneath. So I kind of feel that there might be a solution, but that's it. And now in 5 minutes, I'll tell you all the things that I don't know about Lie algebra and stuff. So Lie algebra in physics, you basically have a state that makes an infinitesimal time step. You have a generator for the transformation, and you have t, that is the time parameter, or this is the parameter of the transformation. And in classical mechanics and quantum mechanics, you have these skew symmetric brackets that tells you how an observable, how a linear functional is changing with respect to that infinitesimal transformation. That's the thing that we want to generalize. So in principle, since you know the linear functional comes from integration in the classical case, in the quantum case, the kind of trace operators, we can just define a bracket that it's the Poisson bracket in one case and the commutator in the other case, and this is going to be a linear functional. And now we can write this in general. In both classical and quantum mechanics, we have this relationship. Right, these are the type of things that I think Marcel can tell me more how they work. So it's easy to show that these in general would be a Lie algebra because the trace and the integral are linear. So all the things just bubble up. The thing that I don't know is whether it's a Poisson bracket, because a Poisson bracket has to act as a derivation of the associative product. And I don't know what is the associative product because I don't know how to generalize the product from classical and quantum mechanics. And it's not the product of the statistical variables because the expectation of the product is not the product of the expectation. It'd be nice if it were like that, but it doesn't work like that. And so one of the questions is that can it be defined in terms of the generator or the composed transformation? And can we define non-commutativity of the observable based on commutativity on the composed transformation? So these are all the things that I don't know. Is there a way to look at all of this in a more general setting as saying, oh, you just have a generated transformation on the ensemble space, and of course you're going to need the structure to describe this thing, and therefore the product comes from the composition, because these are maps. You can compose maps. Composition is a product, forms a group. There it is. I have no idea if it works. And so then the question is, what is the actual axiom that I need to be able to generalize this equation? And because again, like the dream would be to write Hamiltonian mechanics at the level of the ensemble space without knowing whether I have a classical space or a quantum space or a field theory. I just have this generalized Hamilton's equation because I have all the structures underneath. And if we're able to do it, then we know that we have the right space. So one of the interesting things is that both these evolutions are deterministic and reversible transformation. They leave the entropy unchanged. So there is definitely a link between, if it's a new axiom, there is a definite link to the other axiom before. And also this structure guarantees us that there are always stationary ensembles under each deterministic and reversible transformation. So if I have a Hamiltonian, I can always define Boltzmann distributions, and those are going to be fixed points of these transformations. And so the question is, axiomatically, can we turn this around? We already assume that ensembles must be equilibria to have an entropy well-defined, otherwise they don't. He's assuming that every ensemble is a stationary state of some time evolution enough. Does that give us something that then we can turn into axiom and get this structure that we don't have? And that's it.
It's a lot to digest.
Yes, we have, we have 2 days, which is, of course, it's gonna be enough. So I don't think, like, I don't expect everybody to digest everything. Like, what I hope is that there are enough pieces that are interesting that then we can, we can say and flesh out. Okay, so we should go to Marcel.
Yes.
So I will stop the share here.
See if I can share my document.
A quick question.
Yes.
You didn't discuss about composition of ensembles.
Yeah. You notice that?
Yeah, so because that is another point, because you don't know how to do composition, no?
Right. And right now I'm trying to do as much as possible without knowing that. Even the entropy, a lot of the time it's derived, the Shannon entropy is derived by using composition. I don't use composition, you don't need it. So that's part of the game. Like, how far can I get before I'm forced to talk about composition? Because I think a lot of things that people do, they don't require a composition at all. And again, it's not just a matter of having some axiom, it's to find the minimal structure required that it's the game. Okay, so I can make this. How did I make this full screen?
Just a little bit,
On where?
the screen,
On the Zoom screen? Oh,
But none.
and then, yeah.
okay, this is working.
Can you see it?
Yes.
Okay. If I put it in the whole screen, then I cannot see anybody in the room. So I think I will just leave it this way if it's clear.
Yeah, that's fine. I think that's big enough.
Okay. So I will start from a point that is much more advanced than the foundations really. And what I want to talk about is some of the lessons that you get when you look at mixed classical quantum systems, hybrid systems, regarding how the Lie algebras are incorporated there, how you define observables, how you define structure that is common to classical and quantum mechanics, so that you can basically define a hybrid system. And just to give you a little bit of a feeling for hybrid system, well, before I do that, I will first talk about quantum classical interactions in general. That will be very short. And then I will give you two examples. One is ensembles on configuration space, which is an approach that we developed with Michael Hall, and which allows you to deal with classical quantum and hybrid systems where the observables are functionals. I'll be more precise about it later. And a more recent approach, which is hybrid Van Hoff theory, where everything is formulated in Hilbert space. And they bring out quite a number of interesting points regarding Lie algebras, observables, and product algebras in these type of systems. I don't think I'll have time to go into the geometry of ensembles on configuration space. That it's an interesting thing in itself, but I think with the other two topics, it will be sufficient. The time will be used up. Now, quantum classical interactions, one can get an idea of what's going on by looking at these pictures. You can think of classical mechanics as being a lion, quantum mechanics as being an eagle. They each have their own realm. They're each powerful creatures. And if you put them together, you'll get some fantastic animal. It could be a Alpinicus on the left, a Gryphon on the right. And the question is, how many ways can you put these two things together, and whether this fantastic animal is something that you can consider real or not, in some sense. And there's some good reasons for doing this. There's some practical applications in some complicated quantum mechanical problems. It pays off to model some of the system classically. But in this case, you want to do it in a way that is consistent, that you can understand the approximations and things like this. Another reason to look into these hybrid theories is basically the fact that we have work in progress. There is no quantum theory of gravity. And one would like to know what happens if I try to couple quantum fields to classical gravity in a consistent way. What comes out of that? And even if you believe that gravity should be quantized, it still might be useful to look at hybrid models as a step towards a quantum theory of gravity. And the other place where it has relevance is in foundations of physics. But here one has to be careful, and that's why I put a yellow light there, because it's not always understood that there are many ways of bringing together classical and quantum mechanics, so that many of the conclusions that you derive from these hybrid models are model dependent. And there are claims that you cannot do this, you can do that with a hybrid model, but the proofs always depend on a given model. So one has to be careful about that. And I will discuss two models which have certain properties which I think are reasonable, and which then gives you some, hopefully will give us some insight into these Lie algebra structures and product structures. So you can imagine the difficulties, the mathematics and the conceptual issues that you deal with in classical mechanics and quantum mechanics are very different. You're using different mathematical structures. You have to find a common ground before you can define a theory that is a mixture of classical and quantum systems. But more difficult are the conceptual issues. That is, there's a number of things like an uncertainty principle that we have in quantum, not in classical, superposition principle. There's a lot of properties of classical mechanics that we have to decide whether we preserve them or not. So there's a question of what's known as classicality. How do you define classical systems? And then how you describe quantum systems. And this, I think, it's important for foundations when you're trying to build up from the bottom up classical and quantum theories, to try to identify what is essential of these theories. And as I mentioned before, there are many, many variations on a theme. So let's look at two approaches and see what they can tell us about these structures. I'll talk about ensembles of configuration space, classical, quantum, and hybrid. With Michael Hall, we wrote a book about this. It came out about 10 years ago. And most of the material I will discuss as far as ensembles and configuration space is concerned can be found in this book. So you have this as a sort of a general reference. I will go a bit more in the details now. So please, if you have any questions, go ahead and interrupt. And if not, I will just continue. The basic idea that we have here, and as I said, it's higher level than most of the talks or the concerns of the workshop. The basic idea is that you have some physical system that can be in different configurations. And you assume that you can introduce a probability density that tells you the uncertainty of the system being in one or another of the configurations. The second assumption is that you will have time evolution. That is, the system will do something, otherwise it's not a very interesting system. And the assumption here, which is also a strong assumption, is that you have an action principle. So you can have a Lagrangian, but you can also, for our purposes, we will introduce what's known as an ensemble Hamiltonian. So given P, which is the probability density, which is the field, then we have to introduce a canonically conjugate quantity. And some functional of P and S will be what we call the ensemble Hamiltonian, or will be the object that generates changes.
Marcel, I have a question here.
Yeah.
So you have a probability distribution only on the Q, and then you have a canonical conjugate, right? Typically, you would have in Hamiltonian mechanics, you would have a probability distribution on both Q and P. So how does the distribution Q and P relate to the probability on the Q and the conjugate?
Okay. This is basically what will come out of this when you stay in classical mechanics is the Hamilton-Jacobi formulation of classical mechanics.
Right.
And this is connected then to the Hamiltonian formulation of classical mechanics by just introducing the momenta and so on and so forth. It turns out that it's possible to also define ensembles on phase space. This is something that is quite recent that we didn't realize until a couple of years ago. The relationship here is that you can introduce mixtures of these probabilities on Q, and these will correspond to phase space mixtures. If the mixtures depend on the parameters that give you a full solution of the Hamilton-Jacobi equation. I'm getting ahead of myself here.
Yeah, let me rephrase the question in a much simpler way. So
yeah,
suppose, so I've essentially on one side, I can give you a row on position and momentum. And here you're giving me a P and an S on position. Is there a way to go from one to the other? Or there isn't, there are two completely different things and I should think them as different things?
No, there is a way to go from one to the other. Unfortunately, I don't have transparencies about that here. But the way you go is the following. Consider a free particle.
Yeah.
Then you can write the solution of the Hamilton-Jacobi. This S will be the solution of the Hamilton-Jacobi.
Yeah.
As m times v times q.
Yes.
It is through these parameters mv that you can bring in momenta now. So you define mixtures that depend on these additional parameters of the solution of the Hamilton-Jacobi equation. And then the probability density for the phase space will be P of Q times a delta function of P minus gradient of S.
Okay, good.
This is how it works.
Yeah.
It's a bit more complicated than that because you have more freedom in phase space than you have here.
Exactly.
But,
that was my worry. Okay, but you have the
yeah.
delta function, and those are the type of things where you can.
Yeah.
Okay.
And then you take mixtures because you can have different solutions, functional forms of the Hamilton-Jacobi equation. So you take mixtures of solutions.
I think you can go on. I think that's what I wanted to understand.
Yeah. So this is described for particles, but the same approach works perfectly fine for discrete systems or for fields. One can also do field theory in this way. And what you get is that this so-called ensemble Hamiltonian is going to cause a change in P and S using the Hamiltonian equation of motions. But up to here, there's no physics yet. This is just saying I have a probability that evolves in time. I just have dynamics of probabilities. And to put in the physics, what you do is you choose particular ensemble Hamiltonians. So for example, here's the case of two classical particles. You can recognize that in the square brackets, you have a Hamilton-Jacobi expression. And if you calculate the equation of motions, for S, you get the Hamilton-Jacobi equation, and for P, you get a continuity equation. So it's through the choice of ensemble Hamiltonian that you have now made this abstract system into the description of two classical particles. And if I choose a different ensemble Hamiltonian, I add this term to the classical ensemble Hamiltonian, which is sort of like a Fisher information term. Then you can compute the equation of motions, and these are just the Schrödinger equation and Malalung variables. And then you get just the Schrödinger equation. So the main difference here is that you have particular choices of ensemble Hamiltonians that will give you either quantum physics or classical physics, but the space is basically the same. It's a space of two functions, P and S.
Okay, let me here. So you literally have the same type of functions for both classical and quantum mechanics. You're just changing how the Hamiltonian is defined, correct?
Up to here, yes, but we'll see that one has to put certain restrictions. So we now introduce observables. The ensemble Hamiltonians are observables, and observables are any functional of P and S that have to satisfy certain requirements. So we require that if you use this observable as a generator of transformations, probability should be preserved. And this gives you, for example, gauge invariance, that you can add a constant to S, and the observable should not change. One can show this. In our formalism here, observables are both expectation. We'll see they're both expectation values, and they're also generators of transformations. So they play a dual role. the same way that in phase space of classical mechanics, you have this dual role, and in quantum mechanics, you have this dual role. In this space of these two functions, P and S, you have that. And one thing we require of the observables is that they be homogeneous of degree 1 and P. And in this way, we can interpret this as an ensemble average. So one has to restrict the possible observables so that you preserve probability, and also you can interpret now these observables as expectation values. And what you find out is that you have two different sets of observables that describe different systems. So to recover classical mechanics, to recover the correct expectation value for classical mechanics, you use the expression here on the left for the observable for a function f. And you can see, since the gradient of s is essentially the momentum in Hamilton-Jacobi theory, then you will get the correct expectation value. And for quantum mechanics, we will define the observables as expectation values. Here I've introduced wave functions. And if you calculate this expectation value of this operator M, it's essentially an observable. It is an observable that depends on P and S. And what you can show now is that if you just restrict to the set of classical observables, it's a closed set of observables. And this Poisson bracket, which is defined in the space of functions of P and S, turns out to give you an isomorphism to the phase space Poisson bracket of functions of f of Q and P. While if you choose your observables in the other way to get where you have a quantum operator, then this Poisson bracket gives you results where you have an isomorphism with respect to the commutators you get, for example, for the operators of quantum mechanics.
Okay, so this is, I guess, the part that I want to understand well. So you are defining the observable to be something, and then you derive that the Poisson bracket is the specific ones, correct?
Well, we are defining the observables to equal the expectation values the way we know how to compute expectation values.
Right.
And what is perhaps surprising, or perhaps not, to me it's still a bit surprising, is that we have this property that if you restrict to classical observables, then this Poisson bracket in the space of functions P and S gives you an isomorphism to the classical Poisson brackets. And if you restrict to this quantum expectation values, then you get an isomorphism to the commutator algebra of quantum mechanics.
Right, because you defined the Poisson bracket before as the equation of motion. So you basically say, I have these symbols that represent things with an equation of motion. And
Right.
then you say that they have to have some of these properties that you said before. And then you say, okay, in this case, I take these symbols to mean this particular expectation. And then you find, that original Poisson bracket that I have is the Poisson bracket itself. Okay, it works.
Right, yeah. So, so this gives you a space that contains both classical and quantum mechanics, in this sense that you get the equations of motion either Hamilton-Jacobi with a probability over configuration space, or you get the Schrödinger equation and you get the whole algebraic structure of quantum mechanics. And what's interesting is that this gives you an invariant, or gives you tells you why the classical particle is different from the quantum particle. They obey different algebras. We know that the Schrödinger algebra cannot be mapped one-to-one to the Poisson algebra, only up to second order polynomials. This is the Grunwald-Van Hoff theorem. So these sets of observables will be different if they correspond to a classical particle or a quantum particle.
Yeah,
But
so,
nevertheless, the mathematical framework is common to both.
right. So I think, like I'm realizing right now that you have a bigger piece that I need that more than I thought. Because so if I'm able, so from the previous three axioms, I have a general structure, right? And then I say, and then I'm gonna find some specific axioms that will force on the classical side the space to effectively be a simplex and therefore have you know the structure like that. And on the quantum side to be the space of density operator. So if I'm able to do that, and then I would know what my linear functional would be that it would correspond to this. So once we put essentially the fourth axiom would be something along the line of what you have. So if the condition on the previous axiom tell me that on the classical side my expectation are like in the first case, and on the second case you give me the other one, then automatically you have the piece that tell you, now your Poisson brackets are gonna follow.
Yeah, and this also works for this Hilbert space formulation that I will show you later.
Okay, so I'll shut up and let you talk.
No. No, this is it's a good point, and it also kind of helps me move things ahead, because this same absolute distinction between classical and quantum that comes out here will appear again when we look at this Hilbert space formulation of hybrid mechanics.
And sorry.
Yeah.
Just a quick question. So what is exactly x prime in that equation there?
I just run out of space to write s as a function of x or s as a function of x prime. So I just put the primes on the functions rather than in the coordinates. They really mean that the function is either a function of x or a function of x prime. But it's a good point because the notation that I use is not very good here.
And are
so you just
real variables, or I used to be, or
so x is the I should mention this here. In cases where I have a distinction between classical and quantum, or I have hybrid systems, I'm using Q to denote the configuration, the coordinate of the classical configuration space, and I'm using X to define the coordinate of the quantum configuration space. I forgot to mention that. So basically, it's just a coordinate for the configuration space, but I need to keep them separate. Did that answer the question?
Yeah.
Okay. One thing that comes out of looking at the transformations that are generated by S is that even though we introduce this in an abstract way as just a canonically conjugate coordinate to P, it turns out that the expectation value of the gradient of S is the infinitesimal generator of translations. And also because we have this imposing this property that the observables be of order 1 and P, then one can also show that it's a local energy density, or the time derivative is a local energy density. So this is interesting. This comes out after you've built the formalism, this interpretation of S, which was introduced here axiomatically. And this is valid for both classical and quantum, these expressions. And if you want to now define a hybrid ensemble Hamiltonian, then you do what you usually do in mechanics. You have the Hamiltonian of one particle, the Hamiltonian of the other particle, in this case, a quantum particle and a classical particle. And then you define an interaction term, which for this example, I've set it equal to a potential term. And what you get then are equations of motions that are neither classical nor quantum. Well, you get the continuity equation, but this modified Hamilton-Jacobi equation is neither classical nor quantum and has to be solved separately. So you have back reaction of the classical and quantum system, and you can have changes generated on the classical and quantum system by this interaction term. And as far as defining a probability for the classical or quantum particle, it is straightforward because you just integrate out the other coordinate. So there's no, in this sense, it's very intuitive for what we know from handling probabilities of composite systems. You can couple, we've looked at oscillators coupled to qubits. We've looked at oscillators coupled, a quantum oscillator coupled to a classical oscillator. We've also looked at a classical space-time, classical gravitational field coupled to a quantized field. You can do all of these things here. And but I think what is perhaps most illuminating here is to see how this Lie algebraic structure emerges and how it becomes an important part of this distinction between classical and quantum, in how the definition of observables plays an important role here. You have a bigger space that encompasses both a classical system and a quantum system. But rather than give you examples, I would like to move on to the other formalism I want to show you in Hilbert space. Are there any questions at this point?
Well, this is very nice.
Okay, thank you. So this other theory, hybrid Van Hove, is quite recent. We're still working on it with my colleagues Andres Bermudez and Sebastian Ulbricht. And we're trying to understand it better. I think there's an interesting point that has been lost because it's a historical point, and all of a sudden it kind of played a big role in what we are doing here in this Hilbert space formulation of hybrid systems. Turns out that Dirac in the 20s came up with what he thought would be 4 basic requirements for operators that should represent the classical quantum operators representing the classical observable f of q and p. And he said, well, they should obey the linearity rule. We should have a power rule. That is, if I have the operator of momenta and I want the operator of momenta square, I just multiply the moment operators 2 times. And if I want the momenta cube, I just multiply the momentum operator 3 times. The identity rule, and what he thought was possible and desirable was to have this a rule that says the commutator is going to give you a representation of the Lie algebra of the Poisson brackets. And already Heisenberg wrote to him in a letter that he didn't think this was possible, and he was looking at higher order polynomials. And finally, it was established that these 4 requirements are inconsistent. That is, you can satisfy 3 of them, but not all 4. And the Groenewold-Van Hoff theorem tells you that the Schrödinger operators do not satisfy the 4th rule. That is, up to 2nd order polynomials you can match, but if you go to higher power polynomials, then you get a discrepancy, and it cannot be fixed. Now, if you now look at this from the point of view of wanting to formulate classical mechanics in Hilbert space, you definitely would like to have the 4th rule, because you would like to have a representation of the Poisson bracket, Lie algebra, in Hilbert space. But this means that one of the other rules has to go. And it turns out that these Van Hove operators that I will mention now have satisfy the 4th rule. That is, you have an isomorphism between the commutator of these Van Hove operators in the Poisson bracket, but you don't have a power rule. That is, you don't have a product algebra. if you multiply two operators that represent observables, what you get is not an observable anymore. And I think this is relevant to this issue of whether you should, whether you can have a product or not. Everything works fine with commutators. That is very well defined, but the product of two of them are not defined. And this has consequences and kind of saves the day when it comes to doing this reformulation of classical mechanics in Hilbert space. Now, the basic idea was to take the unitary representation of contact transformations that Van Hove developed in the 50s. That was his thesis. He looked at transformation of the phase space that left this differential invariant. So this is what defines a canonical transformation. DS is defined in a particular way. And he constructed representations of this group. And it turns out that you have reducible representations, a whole family of them that are labeled by a real parameter alpha. And if you choose this alpha equal to 1 over h bar, this is something that Van Hove showed, then you get a formalism that is very close to quantum mechanics in some sense. But it's really a classic, the operators have the Poisson algebra, Lie algebra. And this h bar that is introduced here has nothing to do with quantization, it's just one possible choice. And the way you proceed with this is if you have a function in phase space, you have an associated Hamiltonian vector field that you can define. And the way Van Hove defined his operator was to, is expressed here. Basically, it's a first order partial differential operator. And you can already see that if you multiply two first order partial differential operators, then you typically get a second order partial differential operator. So it will not be in the family of Van Hove operators. So therefore, you cannot take the product of two observables and get another observable. You can always take the commutators and get an observable, but not the product. And there's some issues here that there's some functions in phase space that will not give you a complete vector field. So in this case, these operations are not self-adjoint. They cannot be used arbitrarily to generate transformations, but they are perfectly okay as observables. Or within a limited range, they can be used as generators. And what you can do then is introduce classical wave functions, which depend on Q, P, and T, define an inner product, and basically do classical physics in phase space. In Hilbert space. I won't go through this proof. I'm just showing this to tell you that it's straightforward to show that the commutator of two Van Hove operators gives you an isomorphism with the Poisson brackets, but it's very tedious to work it out. But it can be done. It's in one of our publications, something in Van Hove, of course, already established. You can try to understand how the classical wave function is put together by essentially having the equation that the time change of the wave function should be just the result of operating on the wave function with the Hamiltonian. And since we have the prescription of Van Hove of how to define all the operators for the functions of Q and P, you can write it down like we do here. And if you introduce Madelung variables, you get two equations. The equation for the density is just the Liouville equation. So you're getting classical mechanics against. And turns out that the equation for the phase is nothing else but the equation satisfied by the classical action. And this is a big difference with one big difference with quantum mechanics is that these are decoupled equations. So they're not, you can solve one and then solve the other one. And you don't have the situation in in quantum mechanics that if you solve the Schrödinger equation, you solve simultaneously for the phase and the amplitude. And as a matter of fact, the phase is not uniquely determined by this equation that we get for it. You can always add some function of the Hamiltonian in tau minus t, where tau is basically the time over a trajectory expressed as a function of q and p. So if you think of classical trajectories, then you can identify the time with some function of q and p. So
Go back to the previous slide.
yeah.
And this the couplings. So the first one you say is just a Liouville equation.
Mm-hmm.
And the second one is the coupled, meaning that so in both direction. No, because the second one has the row. So the second
Well,
one. Oh, but it filters out, so it doesn't.
I'm putting it outside of the bracket because it turns out that it will be useful to have it in this form.
Yeah. So so basically, solving one tells you nothing about the other. Right? So if you solve they're basically two completely decoupled systems. What the probability distribution has nothing to do with what the action is doing.
Exactly, but it turns out that there's good reason to well, this would mean that given a solution of the Liouville equation, you could add any phase to the wave function as long as it solves this equation. But it turns out that there's a way of fixing the phase of the wave function and getting a unique thing. And this comes out when you now go one step further and said, well, what are the expectation values of these operators of Van Hoff? And it turns out that if you calculate it, you get the first part, which is just what you would want to have, the average of this function f over the density rho. But then you have an additional part, which is zero if the phase of the wave function has these nice properties, which is anyway properties that it will have if you identified with the action.
Okay.
Because the differential of the action is p dq minus h dt, and you have this type of behavior. I mean, you have this type of things. And what you need to do is you cannot take any arbitrary solution of that equation for the phase, but it turns out that you can set sigma to this expression that I'm writing here. I introduced two functions, eta, which solves the equation for the time-independent case. So eta depends just on q and p. And I also introduced tau, which is basically the time, would be a time a function that gives you the time in terms of q and p over a given trajectory. And if you define sigma as eta plus h times tau minus tau 0 minus t, then you can see that over classical trajectories, you satisfy precisely the constraints that you want to satisfy if you want to have the correct expression for the expectation value.
Okay, so basically the way that I would say it, if it makes sense to you, you basically have a gauge indetermination of on the Lagrangian and on the expectations, and that's where the decoupling is. Then you fix that gauge so that you recover these things, and then everything works out. Okay.
Yeah. As a matter of fact, these equations of this formalism of Van Hoff comes from has been used a lot in geometric quantization. And there's a group in England, Cesare Tronci and his group, that have been looking at this, and we have kind of reproduced some of the equations, but they've taken the route of gauging, allowing for a gauge freedom, which makes the formalism much complicated. Well, we have gone the other route and said, well, we're going to use this to fix the phase. And turns out this has some nice consequences.
Yeah, there is a similar problem in classical mechanics, so that because momentum, conjugate momentum is defined up to a phase. Then in physics, we just don't care and we always fix it, so on. But then there is
Right.
a similar problem, so.
Yeah, here what you have is you find out that the phase of the classical wave function is essentially the action, but if you interpret it as the action, it has to satisfy certain constraints, which are the ones in the last line here. And something has to be fixed, because once you have the action, you can also take the gradient of the action, and that is the momentum. So you have too many ways of talking about momentum in this formalism. And fixing the phase in this way gets rid of that problem.
Yeah.
Now,
I just
what
wanna-
this also gives you is that if you require that the phase have a
Second,
particular,
Marcel,
I
one second.
Yeah.
just wanted to quickly check on the time, since we had scheduled a coffee break now. It's a 30-minute break, so we can shorten it a bit and still keep on time for Susanna.
yeah,
I see you have 63 slides listed.
yeah, that's because I put all this other
Okay.
topic, but I'll be done in 3 or 4 flat slides. Yeah.
Okay, yeah. 10
yeah.
minutes, 10 minutes should be fine.
5 minutes should be enough. So one thing that comes out of fixing the phase is that you don't have a superposition of wave functions. It's not allowed anymore, because the superposition will not have a phase with the right functional form. And this is good, because you don't want superposition of classical systems. You don't want interference, you don't want superposition. And this is a result of fixing the phase. The other thing that's happened is that another thing that happens here in this formalism, and this comes out because you don't have a product algebra, is that you could wonder, how come if I have commutating observables Q and P that give you IH bar, why don't I have an uncertainty principle? And one way to look at that is to go back to the way, for example, the uncertainty principle is derived in Landau and Lifshitz, and basically you define a special ket, you assume states that satisfy this to make life easier, and then you can define this quantity which is positive, and you can get then a limit on this expression that's at the bottom. This is the normal way of deriving the uncertainty principle. However, in quantum mechanics, the square Q times Q is Q squared, and P times P is P squared. But with Van Hove operators, this is no longer true. As a matter of fact, if you multiply these two operators, you get something that's not unobservable. So this means that while this expression at the last line is mathematical true, it doesn't contain the physics of the uncertainty principle, because you cannot interpret this as the operator that represents the Q square. And this is what allows you to bypass this. And as a matter of fact, delta functions are or approximations of delta functions are perfectly okay here as densities for these wave functions. I think, yeah, so you can now define hybrid systems by taking a classical particle and adding a quantum particle with configuration space coordinate X. And then say you use the Schrodinger representation. And one nice thing is that the operators that represent observables for the classical particles commute with the operators that represent observables of the quantum particles, because they act on different configuration spaces. And one can define interaction terms that are well defined, and one can get then a hybrid type of Schrodinger equation that describes then two interacting particles. I think basically done here, but I think the message here is that it is possible to have a larger space that includes both a quantum and classical particle, but this distinction between quantum and classical is going to come throughout the observables. And if we have either a Poisson bracket of functional of P and S, like in the first case, or if we have commutators of operators, like in the second case, the distinction between the particles will be given by how you distinguish between classical observables and quantum observables. And this becomes an essential part of the formalism. There are other approaches where you say, well, in Hilbert space, all classical observables commute. And then you completely lose the Lie algebraic structure, and there's very little you can do with it. This is the Kuhlmann von Neumann approach. It becomes quite complicated. And the one thing that comes out of here is that if you're going to work in Hilbert space, it doesn't mean that your classical observable must be commuting operators, because in this case they don't commute, but there's no problem with the uncertainty principle, because you don't have this product algebra, which you need to prove the uncertainty principle. Okay, my 5 minutes are up. I think I'll stop there. And if there are any questions.
Yeah, we can take several minutes for further discussion, if that's helpful for anybody right now.
Well, I will want to see how how it works, how the first part of the ensemble spaces on field theory works, but I don't think it's going to be a 5-minute thing. So
no, but I can give you a preview.
yes.
Basically, you have the problem that you have to define now integrals in this spaces of functions, space of fields.
Yeah.
And for example, when we looked at this, then becomes very formal. But when we look at classical gravity coupled to quantum fields, there is a natural metric on the space of gravitational fields, which is the DeWitt supermetric. And from here, you can get a volume element that is quite restricted. There's not too many choices. So formally, you can use this, and you have functional integrals. And it becomes very mathematically non-rigorous. But the idea is to follow this approach where you say, well, now I'm going to have, instead of this ensemble Hamiltonian that's a function of P and S, now it's going to be a function of fields.
It's not the Q's that are becoming. Oh, okay. So I thought that you have a P of Q, and it would become the P. The P of opposition, and becoming the P of a field. It's not.
Yeah. This is what you will have. You will have the P of a field and the S of a field.
Okay, good. Yeah.
And then you have to define this ensemble Hamiltonian, which is a functional integral over this functions of fields.
Okay. You say it becomes a little bit mathematical sketchy, but you sort of do the let's say a pattern substitution, and things work out in the end.
Yeah, and what you end up is, in the classical sector, you get, for example, you get a Hamilton-Jacobi equation for the fields. So you get the Einstein-Hamilton-Jacobi if you're doing gravity, or you get Hamilton-Jacobi formulation of a scalar field and things like that. And in the quantum sector, you get the functional Schrödinger equation. So this is the things that play a role in for particles. You have a Hamilton-Jacobi equation, and you get a Schrödinger equation in Madelung variables. For fields, you get a functional Hamilton-Jacobi equation in a functional Schrödinger equation.
Yeah, and you haven't tried to do all of this on the extended phase space, where the H becomes the Hamiltonian constraint, and your Q's are both Q's and T's, right?
No, I haven't tried that. Yeah, that's correct.
Yeah, there will be a million things to, I think that, Sure.
Okay, but then I would propose we take our coffee break. We'll resume at 11 at the originally scheduled time, which is 11:20 here. So in 21 minutes for Susanna's talk.
Okay.
Yeah, and Marcel and Susanna, if you send me your slides, I can post them on the website.
Okay.
So
Thank you.
I wonder what to do with the live stream. We don't really have a way to pause this, because if I end it, it's gonna be closed. Maybe I can disconnect. I'll try disconnecting the stream. No, but if I disconnect the stream, it's gonna end the stream anyway. I think I'll just you guys can go and start.
Oh, yeah.
the rest. I'll figure out something.
It's a bit too much.
Okay.
Robust.
Okay. Okay, let's see if this is working still or. Let's one camera. Okay.
Some coffee, Alice.
Ah, there you go. Still the coffee, still the coffee. Okay, so it's following me. Oh. And streaming has resumed. Okay, we're waiting for the other people to come back and then we can restart. So Susanna, there probably was too much physics for you in the last talk.
Yeah, I'm getting used to. Maybe I can try share, or it's my turn, I guess. So I can share my slides.
Yes.
So
start doing
if
that
it's
and then-
working or not. I can see myself, but not my slides. So
I can see your slides.
okay, great then.
And here they are your slides. So you're set.
I think I can see.
Okay, great.
Attendee.
Ah, probably. Yes, you are an attendee.
Yeah, and then, okay. Selecting one. I know.
Okay, so you should be upgraded now. And they're waiting for an S, so he's like, let's live. He's up here, he's getting food. So this- Okay, I think we are all here. Susanna, you can go.
Okay, thank you very much. Hopefully you can hear me well enough to understand. Okay, so once again, hello from far Slovakia. Well, my part of this workshop is talking about the measure theory or the, or to be more precise, non-additivity measure theory. So I will introduce you to the world where 1 + 1 does not necessarily equal 2. And since I already talked with Gabriel and Tobias and heard few presentations, I also went through both of your papers, then I somehow realized that there are probably just three topics I can focus on that can be helpful for your focus. So the first I will talk about non-additive measures as some kind of a basis for everything that you're doing regarding measures. Then I will talk about integrals with respect to these non-additive measures, and then some kind of inverse problem to the integration, and those are measure derivatives. In all three will be just about non-additive background. Okay, this is not working fine. So I will have some kind of sample space and the corresponding sigma algebra, and then and I will consider a set function, so just a function that assigned to any subset of the sample space assigns some real value. In general, mathematicians are mostly talking about measures when we have two additional conditions. And the first one is groundedness, so to empty set we keep 0, and then we have a non-negativity, meaning that every measure value needs to be at least 0 or something bigger. This is just the natural assumptions for, since the measures came from physical measurements. So if I want to say how tall I am, it will definitely be non-negative number. And if I'm not measuring, then I will get 0. So these are just very natural things, but while giving further conditions, we can get some other types of measures. So for example, if we add additivity, so measuring two sets separately will give us exactly the same value as measuring them in total or somehow connected, will give us the additive measure. So groundedness, non-negativity, and additivity are the conditions for the additive measures. Important is to say that these sets or agents A and B need to be independent. So there are no interconnections between them, and then we can talk about the additive measures. And the most common additive measures are just a Lebesgue measure, which is probably very, very common. In the most the easiest way it can be taken on the real line. So for a real interval, closed interval, it's just the difference between the boundary points. And the other additive measure that is very common is a probability measure, where we have a distribution function. And if that's differentiable, then we have the density function, this is the small p, and then probability of, again, on a real line. So for some closed interval, it's just given as a difference between distribution functions, all of the boundary values or the boundary points here. I already mentioned that here A and B as sets or agents needs to be independent, and that's kind of a problem in the real life situations, since there are many cases where they are not independent and somehow interact with each other. For example, if there are two co-workers working on a paper together, then collaboration means that, well, if they write the papers independently, would probably be less than if they write the papers together. So this equality here is somehow too restrictive for a real life situation. And that's why non-additive measures were assumed. And the only condition that is still there is that we are weakening the additivity property to the monotonicity. And it's also natural condition since, okay, if I get back to those collaborators working on a paper, it doesn't make sense to collaborate if whatever we are doing together is less than what I can do alone. So this is kind of a natural condition of monotonicity to assume in real life situations. So having the groundedness property and non-negativity property from here, together with monotonicity, gives us non-additive measure. It's sometimes called also fuzzy, but it's very fuzzy name, so non-additive is probably a bit better. There can be also some other conditions, for example, normalization. So for the whole sample space, we can have one, but that's not necessary for whatever I will talk about right now. And well, some examples of these non-additive measures are what I will need. For example, anonymity measures, where we have fixed set E here. And then if the set we are measuring is consists or this E is a subset of this A, we get 1, otherwise we have 0. There is also, for example, power measure that is very common in the applications, where this is only for discrete sets. So on a discrete sample space where we take the number of elements of set A, number of elements of the whole sample space, and then just give it to the power of k, where this k, of course, depends on the applications that we are using it. So it can be changed according to what we really want to study or what to measure. And what we are dealing with mostly is the continuous case. And there, the most common measures that we can say are distorted measures, saying that we have some kind of a distortion function, M, which is a non-negative increasing function with some boundary conditions so that the result is also measured. And we make a composition between this distortion function and some additive measures. So for example, the Lebesgue measure or probability measure. Of course, these resulting measures are non-additive, and they have some properties. But again, we can change this M function, so this distortion function, so that the resulting measure has some wished property that we want. So for example, if we take convex or concave function as this distortion here, we can obtain a sub-additive or super-additive measure. So something which gives us not the additivity property, but something with the inequality sign there. Okay, and since I was reading some of your papers, and I came across some sentences that you had there, that maybe you have non-monotone measures. So we have only the groundedness and non-negativity, but monotonicity, even monotonicity is somehow violated. This in our community is called non-monotone measures. So no monotonicity is there. And this is kind of common in a decision making when, for example, you have one kind of a spy in a coalition that ruined the whole decision making process. And I asked Gemini if that's a thing in physics, and said that somewhere in the quantum mechanics, when you're dealing with negative interference, then it can be that the whole will just become zero when some agent comes to the play. So non-monotone measures are also the case in measure theory. They're also studied, and of course not that as well as for monotone measures, but there are also some results there that can be used in case you found out that your measures are non-monotone. And in the paper, Gabriel also mentioned the sign or the measures which have both positive and negative values. There is also a thing in measure theory, and we are calling these signed measures. They very naturally arise when we are subtracting two measures that can have both positive and negative values. And again, I was Googling a bit, so can be used or it's possible to model some kind of physical quantities, so some charges, since we have protons and electrons, and some overall charge or net charge can be also negative. So this is also a thing. This is also something that was studied. We have also integrals or some generalizations or some restrictions of integrals that can be used even for these measures. So I'm not sure if that's helpful, but I found it. So
Give you some context. So for the non-monotone measure, it's actually, before I spoke to you and Vincent, I thought I had a monotone measure, and you guys said, "Oh, it should be monotone." Then I went, "Oh, actually, I can make it monotone and much nicer." So the result that we have was basically for the signed measure. There is a whole representing states with the pseudo probability measure, which are measured as sum to one, but they're signed. And the way that it actually works is that we saw before that ensembles embed in a topological vector space. And so the quantum states, the state of quantum states can also embed in a vector space of measures, of signed measures. So, for example, if you have the block sphere, which is a ball, right? It's not a simplex, so I can't get a tetrahedron that it's exactly that, because the tetrahedron would be the space of probability measures. But I can still fit the ball inside the tetrahedron, or the tetrahedron inside the ball. And the measure outside of the tetrahedron are the signed measure. And so I can still represent state with signed measures. And there is a set of literature that does that just because you have the linear space. And then the expectations are linear. So you basically keep the linearity, but you sacrifice the fact that the measure does not represent anything at all related to probabilities, just a representation. And so what we're trying to do is, instead of trying to find another representation that is somewhat tied not to probability, but this mixing coefficient, but then we need to lose the additivity. So, but this is great. I mean, this is all, I didn't know about the other measure that you said before. So yes, go ahead.
Just for the information, of course, it's easier even for us in the measure theory to deal with monotone measures, because it has then the integration and everything has some nice properties. But just maybe for your information, if you really need it, there exists some, and there are some nice results regarding that. And again, I was trying to get something from your papers, so I was just you're always talking about vector space. I'm not sure if you need a discrete or continuous space, but well, I found, or I'm also using it, that there is a vector space of discrete measures, of all the discrete measures. I already mentioned the anonymity measures somewhere a few slides back, and these are exactly the basis of this. So any discrete measure can be obtained as a linear combination of these anonymity measures, where this coefficient here, of course, depends on the set we are using, and it's should be Möbius transform, so something a bit more theoretical, but still this is kind of easily computed. So any discrete measure can be written as a linear combination of these anonymity measures. And this is probably more for me than for you, but any discrete measure can also be written as a distorted probability. So the classical physics, I guess, works with probabilities. So we can, any discrete measure can be written as a distorted probability or almost distorted probability here, because this f as a function here can have both, positive and negative values. So it's kind of a polynomial. And then we have the composition with the probability. Or if we want to take the only non-negative functions here, then it's just the difference between two distorted probabilities. This is only for the discrete case. Unfortunately, for general case or for continuous measures, we don't really know what's going on there. We have some hints, but it's still ongoing work and it's not going well. So this would be amazing even for our case, for our theoretical studies, I guess also for you, but this is something we don't know, but I will try.
We don't know, it's not that we know that it's false, we just don't know whether it's false.
We just don't know. We have a intuition that it can be also vector space, where this basis is made with distorted probabilities, but in higher dimensions, and that's too technical, too complicated for now to observe for us. But intuition is there. We just, well, don't know yet. Okay, so this was everything for the measures. And now I will skip to the integration. So for additive measures, so Lebesgue measures, probabilities, we have the Lebesgue integral. That's kind of common if we are integrating on a nice enough set and we are having some smooth enough functions that it's Riemann integral, and then we have all the nice properties that we have and all the nice formulas for integration. However, for non-additive integrals, it of course doesn't work this easy. And as you mentioned in your presentation, Gabriel, we have one very nice integral that we are using most of the time, or it's most commonly used, and that's a Choquet integral. So first we need to have a permutation which orders values for the function in a non-decreasing way, sorry. And then we also define some special sets, which takes all the values which with the functional, all the elements with functional values that are bigger or equal to the kth after the reordering here. And then the formula for the Choquet integral is just f of the kth value times this difference of measures for the set ak and ak plus 1. And we sum it up through all possible values here. Probably the nicest property Choquet integral has is that if we take additive measure instead of non-additive, then we get exactly the Lebesgue integration. And this is kind of easily seen because this subtraction here, this difference here, is will for additive measure be just ak minus this ak plus 1, which in fact is just the element a sigma k, or the x sigma k, and that's exactly the Lebesgue integration as we wanted. So probably the nicest property of this integral is that for additive measure it's a Lebesgue integral. And again, this is discrete case. For For a continuous or general case, we have something called survival function, which somehow aggregates information about the measure and function in just one notion. This survival function is well known in finance and insurance, but it's kind of a complement to distortion function, the distributed function. So probability distribution function is just some kind of a complement here, because distribution functions measure the set where f is smaller than t. So the sets that these two functions are measuring are complementary. Also, in the additive case, it holds that the survival function plus the probability distribution function equals the measure of the whole sample space. This, since we don't have additivity here, does not hold for non-additive measures, but still somehow the duality, the complementary property is still there. And well, if we only have a function with only positive values or non-negative values, then the Choquet integral is computed as this indefinite Riemann integral from 0 to infinity of the corresponding survival function. If we have function with both positive and negative values, then we need to somehow divide. So for positive or non-negative values, we have this one. And for the negative values, we have this integral from -infinity to 0, which is a bit different, different formula. But anyway, the interpretation behind the Choquet integral is exactly the same as for the Lebesgue integral. So we take the survival function, and for non-negative function, we take the area below the survival function to obtain the value of the corresponding Choquet integral. Okay, some properties that are very nice are, for example, translation invariant. So if we have f plus k, so some constant k there, we can compute the integral of the function and then just add k plus measure of the whole sample space. It is also monotone, meaning that if we have two functions that we can compare, also their resulting values of the Choquet integrals can be compared. A bit of a problem is with homogeneity. With positive homogeneity, we have no problem at all. But if we have negative one, then we are kind of switching from this second integral to the first one. And that's why just taking out the minus sign from the integral means that we need to change the measure from the original to its dual. And well, some properties that are very easily guessed are that since we are dealing with non-additive measures, there is no additivity with the integral. We can somehow force the additivity if we are assuming a monotonicity of the measure of the two functions assumed, but that's too strict. But still, we can force it. And if we want some weaker conditions, so not additivity, but super additivity, meaning that this equality sign will just change to some inequalities, then we need to assume a submodular or supermodular measure. So again, some additional conditions for the measure. And well, since you're talking about the entropy, I guess you will also need some restriction of domain, so not integrating on the whole sample space, but on some subset of it. And then the integration can be done on the whole sample space, just changing the integration function here with the multiplying with the characteristic function of that particular set. So it's 0 in case we are outside of set A and 1 if we are inside it.
So let me ask you, these are properties that, so you fix the definition of Choquet integral and you find this property. Are there derivation in the reverse that you've set the properties and you show that Choquet integral is the only one that has these properties?
Yep, there is some axiomatization of the Choquet integral. Yes. Thinking now what should be, there is definitely this monotone additivity. Okay. But I'm not sure what other, but yeah, that's very easily, I can just check it very, very easily. So yes, there is an axiomatization of the.
I don't know why I never thought about it, but we so when I saw negative homogeneity, right? Clearly, we don't want that in our case. We want that minus f just become minus of the integral. So that already tells me why the Choquet integral would work. It has a property that is not what we want. and definitely we want the restriction of domain. So I'm wondering whether if we find enough of these property, we are able to narrow down or derive what is the integral that we need.
Well, this axiomatization is done for the shock integral. That's for sure. It is also done for the Sugeno, but well, there are many non-negative integrals that don't have this axiomatization, or just we don't know it yet. So yes, this is the other way you can look at it. But well, if you need, depends. Do you need for your work, do you need only non-negative function, or you have function with both positive and negative values?
They can be both positive and negative, yes.
Okay, because then this is just well, for the positive values it's fine, but for the negative values we have two integrals. In fact, we have symmetric and asymmetric integrals, and the difference is exactly in this negativity of negative homogeneity. So this is, I guess, asymmetric integral. When with taking out the minus sign, we get the dual measure. But symmetric shock integral works exactly as you probably want. So taking out the minus sign will do nothing with the measure. So it can be just.
Okay, good.
So
I didn't know that existed. Thanks.
Yeah. For if the function has both positive and negative values, that is possible to do. There are two variations of that. If it's only positive function, then just this one is what we have. Okay, I will write down to probably send you something about it.
Yeah, so we can retry the integral on the symmetric one. I still think it's not going to work, but we can never, because I think in our example we assumed that the f was positive anyway, right? And so
Yeah,
if that was the case, then of course it wouldn't matter if it's symmetric or not symmetric. But yeah.
In our example, we had a positive.
Yeah, exactly.
Yes.
So I don't think it's going to work, but that we should make sure, then double check.
Yeah, okay. So this was the shock integral. So the second most common is the Sugeno one. The definition is made very, very similarly. So again, some reordering of values, some defining of the set. It's just we are taking not multiplication and summation, just minimums and maximums. The biggest problem of this integral is that it does not reduce to the Lebesgue integration for additive measures. But again, we have it has some nice properties, but all are somehow defined with minimums and maximums, which makes sense. And I found, for some reason, that there is a generalization of the Sugeno integral that can somehow return the Lebesgue integration if we are taking additive measure. And the difference is only, well, while Sugeno has this minimum between t, so the identity and the corresponding survival function, here this Lehmann integral has this phi of t here, where this phi function is somehow constructed so that the Lehmann integral this integral can somehow reduce to the Lebesgue integration, but this is way too technical, and I think you don't want to go to there.
Just knowing that these things exist, like it's helpful.
Okay, and there are, well, many more integrals. Some integrals are based on T norms and T conorms. There are some universal integrals that are only based on they only have some kind of axiomatization, and then they are trying to make the integral or define the integral. Okay, this is Shulker integral with the same idea, just different operations here. What I found, thanks to our latest paper, is this maximal chain-based integral, which the definition is almost the same as for the Lebesgue integral. The difference is that we don't need any reordering of the values. We just take different chains, and the chain is just ordered set, which is created as we take the empty set and then add some element from the sample space. So And adding that element should be always different for every chain. So we add first element to obtain C1, some other element to obtain C2, and so that we get the whole sample space here. And this for one particular measure, which somehow aligns with the reordering of the function, this is exactly the Schokke integral. So we can reconstruct the Lebesgue integration from here, but this has more information in the making because we are using all the possible values of the measure, which is somehow more giving us more information about the whole system. But well, this is also something well, maybe you can just check, but so for one particular chain, this is exactly the Schokke integration. So also the properties would be kind of similar. There are many more integrals, but I'm mostly not familiar with all of them.
Yeah, so
But
paper where you basically define an addition and a multiplication, and then you get an integral based on the addition and the multiplication that you have produced. So it's like many.
yeah, this is probably a bit too technical, but in case nothing will work, you will not find any integrals that are now used. Then you can just use this idea that you have the identity, you have the survival function, and okay, probably not you, but well, some mathematicians will guess or just make those operations so that the properties that you need are exactly what this integral has. So this is kind of a construction that works, and this is made in I think it's called universal integrals, when they're playing with the operations to get what they want for the particular applications. But I'm still hopeful you won't need to do that because this is too technical again.
Right, or if we can find somebody for us. But does that pattern match some like fundamental property that you want integral to have, or is just something that you said because you can do lots of stuff with it?
Depends. It works both ways. There are few communities that are working just in a theoretical level when they're just changing the operation so that they can study because the integral will have some nice properties. But there are people who have some practical application, and they are trying to find the operation to fit exactly what they want. So to fit exactly the properties that they want from the integration. And this is probably something that you may be interested in.
Yeah,
But
if I even knew what type of property they're looking at, I can see, oh, does our integral satisfy that or not? And then we can maybe narrow down.
Mhm.
Okay, interesting.
If the Schokke integral is not working, then I guess this is probably the way.
Okay.
But hopefully not. Okay, so this was the integration, and now just very briefly about what we don't know about the derivatives. So for us, the derivative or finding the measure derivative is just the inverse problem to the integration. So while in the integration, we have the integration function and we have the integration measure, trying to find the result, which is in fact just another set function or measure. For the derivatives, the problem is that we have both the resulting measure and the integration measure, and we want to find the function that we were integrating. In the additive case, or when we are assuming additive measure, this is exactly the Radon-Nikodym derivative, or the problem for finding the Radon-Nikodym derivative. And this is already solved for quite a long time. So we just need sigma-finite additive measures, which have this absolute continuity between them, meaning that every time mu for a given set is 0, also mu for that set is 0. And then we can say that the derivative will exist. The computational part is, well, let's say a bit more complicated, depending, of course, on the measures we are assuming and on the integration set that we have. But in general, this is not that big of a problem. If we go from the additive to non-additive measures, this starts to be a bit more fun. So first, it depends what kind of integral we are assuming. Since the shock integral is the most natural one, we mostly studied that, and there are most of the results regarding the derivatives in the non-additive case is given for the shock integral. So we call this the Shocker-Radon-Nikodym derivative. And well, for derivatives, there are two major problems. The first one is existence, and the second one is finding the formula for some practical applications. So with the existence, there are some results that are kind of interesting. They are kind of old, but still work. So if we take both measures to be submodular, then we know that the derivative will exist. The problem is that submodularity as such is an extremely restrictive condition. So they wanted to find something less restrictive, which was submodularity. However, the authors of this paper, and I think it was Graf, needed to add some other additional condition, and that's the strong decomposition property. I didn't even try to write it here because this strong decomposition property comes from the hand decomposition of the sign measure, and there are, I guess, 3 bullet points that need to be satisfied, and they are extremely technical, extremely complicated to verify for a given pair of measures, even for the very easy ones in the non-additive case. So these are nice results, but not very applicable in the application. So I guess for you, they're also a bit not really helpful. What we were trying to do is to look at it from a very, very different perspective. So we came up with a resulting measure approach, where we just took the particular measure mu here, or the particular class of measures, took the general function f, and we were trying to find the class or the form of the resulting measure. So we had both the form of the integration measure, both form of the resulting measure, and somehow we could come up with the formula for the integration function f here. This, however, okay, even though it somehow helps with both the existence problem and the formula problem, but we have with the derivatives, this is done only for particular particular measures. So we take one particular class of measures at a time, which is, well, gives us some results, but it's not that overall result as are these two. But it's still helpful. We were able to find some very nice results with that. So if we have a particular class of measure or particular measure, we can look at the resulting measure and somehow derive from it the derivative here. And why am I talking about the derivatives? Is that the derivative in the additive case, since it's the Radon-Nikodym derivative, it can be taken as the density function. So for example, for probabilities, it's probability density function. So we are hopeful that with this approach, we can find the kind of a density functions also for shock integral. Well, and I also find in some papers some properties of these derivatives. So still, if the derivative exists, they have kind of nice properties that you can play with, for example, when you're dealing with the entropy. So you can, I don't know, this homogeneities, additivities, maybe this changing of the integration measure is kind of something that in entropy is very, very common and very used. And there are some
That's what I like to have, because in that, let's see, the mu would be the probability measure, and the nu would be the probability measure, and the mu would be the count of states. And so here we'll be saying that we can either integrate the functions on the probability measure or on the functions times the density on the count of states, which is exactly, so that would be a property that we want. So that's actually something that I wanted to ask you specifically. And so the Choquet derivative would have that. And
yes.
I assume it because it's the integral is well formed enough that allows you to do this. Right, so even if we're looking at the integral that is not the Choquet integral, even the fact that we want to be able to write that should already narrow down the type of integral that we should have. Okay.
Yeah, this, if you really need this property, then yes, this is not that easy to prove, but it holds for Choquet integral. I'm not sure about the others, but definitely for the Choquet integral and for non-negative functions, this holds with no problem. Okay, and I guess I showed you all my problems from my research. Not all of them, but at least some that you may be interested in. So I guess that's all from me. If you have more problems to add to mine.
To the list, we add problem to your list for Suzanne.
I'm for further, oh, go ahead.
Yeah.
Yeah,
Well,
speak up.
I have a question, actually for Gabriele, because there was something he said that made me frown a bit, and I'm not sure. Because didn't you say at some point that you wanted something to be sub-additive and homogeneous at the same time? Not just positively homogeneous, but
No, it was on the integral
yeah,
that was needed to be.
yeah.
Okay, it's a problem.
Well, I think if you have, for instance, if you have sublinearity and homogeneity, that forces linearity.
Wait. It was the thing that I thought that it was homogeneity was the negative.
Only for positive, so you have homogeneity only for positive constants, right? That is and if you have a negative constants, you switch to the upper, right?
Yep.
Yeah. So if you want at the same time homogeneity for all the constants, for all the real constants, and sublinearity or superlinearity, then you reduce to linearity. You force linearity. So it's impossible.
Okay, that would be an interesting result.
Yeah.
Okay, so you're saying, okay, let me see if I understand. Okay, so I have my mu there would be a fraction capacity, and it's a subadditive measure. The measure is subadditive.
Yeah.
Okay, and then you say, if I put constants there, right,
Yeah.
I actually will want that the integral of that constant is the constants, because my fraction capacity.
No, that's fine. I meant the negative homogeneity that you have there, where you switch from the mu to the conjugate mu.
Well, no, we don't. The point is that we wouldn't have a conjugate mu. The mu will remain the same, but you get the minus sign.
Yeah. Yeah, but that's fine. That's not a problem. If you force that for the same mu. So if you want the mu and the mu upper or the mu over bar to be the same,
yeah,
for that, then you force linearity.
On the measure.
I mean, then your integral will be linear.
We want it affine anyway.
Will be additive.
Yeah, I think we want the integral to be affine.
Oh, the integral has to be
FNG.
additive, yes.
It must be, because I thought you said it must be sub-additive.
I think we're confusing the measures.
The measure is sub-additive.
And the
The integral, I have no idea, but now that we're arguing, I think it
In
has
terms
to
of F and G, it's affine, right?
Yes.
Those
Yeah,
are two different observables.
But then if you take the integral of an
Oh, sorry,
indicator,
no,
it won't be additive. It won't be sub-additive. It will be linear there. If you have the indicator of disjoint sets.
Right, but again,
Anyway.
No, the thing we have is clear, but I think that the measure is sub-additive. Okay. Whether the integral itself is additive or sub-additive, I haven't made any claim on that.
Yeah, but if the integral is additive and you restrict yourself to indicators, the sum of disjoint indicators, it will be additive too, not sub-additive.
The integral.
No, the measure, because if the measure has to coincide with the integral on indicators, then you have a problem.
Okay,
because
I think I need more time to digest.
Okay.
I can't do it
Sure,
in 30
sure.
seconds.
But,
But
yeah.
that's
But just a
another
remark,
topic to discuss.
inspired by what you said, Susanna, because and what you said, I just did a quick check, and it's fairly easy to prove that That
Good.
works. Okay.
Prove me wrong.
Yeah, that's true. If you have non-additive measure, doesn't depend, sub-additive to be fair, then the integral won't be additive at any point. So if you have non-additive measure, the integral needs to be non-additive. Of course, in general.
If you want if you want the integral to coincide with the measure on events.
But so what we want, the linearity, the F affinity, I don't know, the affine combinations, those are in terms of ensembles that are represented by measures. But mixing ensembles doesn't mean adding the measures, right?
No, absolutely not.
So like you don't see the additivity, right? It's not that you're not adding the observables F and G,
Right.
you are adding two ensembles to get a new measure, right?
Okay, then I can't do.
So that's something very different.
Okay, we have to understand. Okay.
We don't see the linearity here.
Yeah,
that
no,
we're talking about.
yes.
It's hidden
So we-
inside how when you mix ensembles, what the new fraction capacity looks like.
Correct, yes.
So we're talking about additivity, but not adding functions here, but adding measures here.
Well, we're not really adding the measures, we're adding the ensembles,
Okay.
or making a convex combination of them, we get a new fraction capacity. And this is not in generalized, just the convex combination of the two fraction capacities. Like there's something more complicated possible.
Okay,
Very
because there is a property of the Schokke integral that if this measure mu is some kind of a linear combination, a convex combination of other measures, then this will hold in general without any problem.
Okay, so the way that I understand, and probably we have to go through this, but I think we will want additivity because in our case, if I have the expectation value of two things, right? And I sum the expectation values, I should be able to sum them on the integral or as the function, and it should be the same thing because those are going to be affine functionals. I know, but you're right. They're a function. I'll shut up. I need to write it down.
Let's take
Yeah, yes, okay, fair enough.
But it's an interesting question.
Yes, definitely, yes. Because even if we can prove, oh, this cannot be done, it's a result. Like, it's, yeah, okay, we can't do it. That's it.
Discussion. Scheduled talk at 12:15, so we would have 9 minutes if we want.
I try to think if there is any other thing. So intuitively, how should I think about like probably there isn't a way. Is there a way to think about the non-additive integral in some kind of way, or it's really like specifically I have to interpret each integral by itself in its own context? It's like that.
Yeah, I think so. That's yeah. As I mentioned, there are some universal integrals, but that's a headache even for me. You can maybe say what properties you need and just go through all the integrals that are defined. That's probably the easiest way out of this.
Okay.
But you need to know what properties you really need. And for mathematically speaking, what properties you need, because I understand, from the physics side, but
Yeah, so okay, so you need to know the specifics of the measure, what is it representing, because even that is gonna be different for whatever, and then the specific integral, what it's doing, and then you can then figure out what is it, how you should think about it. And it's a problem by problem case, and there is no hope of ever getting a general theory because it's really a problem to problem case.
yeah, it's not, to my knowledge, that's exactly the problem.
Look, 2 minutes, right?
Yeah, we still have 7 minutes. We used to have 7 minutes. If we want.
Write it down.
Okay, you write that down. I'm trying to think if there is other things that I can.
B U for some ensemble, is it P A plus P bar B?
If you speak loud, oh, sorry. Make sure you speak
Does
loudly
that
enough
work?
for the microphone.
I don't know what the space for. The linearity we want is this one, right? This is P F. Should I write it here?
D mu A,
Yes.
so that one you will have.
Yes, but the mu PA plus P bar B is not the sum of those two at all.
Yeah.
It's overly complicated. I don't even know if we can write it in general.
Because if that would be true, then everything. would-
Yeah, it would be a lot simpler. Yeah,
Hmm.
It's not
P mu.
P U A plus R.
Yeah, that's not. Yeah, that doesn't work. Yeah, it's those two things are different.
But,
Because
but then your integral can't coincide on events with the measure.
what do you mean by that?
If F were the indicator of an event,
Yes.
and you would have that the integral of the indicator would be the measure of the event. That's what I mean, yeah, then you would have that equality, clearly. So it would follow, which means that your integral can't coincide on events with the measure. Which is a very funny integral.
Oh yeah, it's gonna be very so.
I don't know of any integral that does that.
So think it like this. Let's do quantum. Say like we have a ball, right?
Yeah.
And you take the two pure states. Okay, then the fraction capacity it's one for every set that contains the pure state.
Yeah.
Right, and it's zero if it doesn't contain it, because that you have to make that. Then you make a linear mixture of the two, right? And so let's say that you get actually even better. Let's get to the you have two orthogonal ones, so on the opposite point of the ball, and now you take the middle point. Right? For the middle point, the measure on each singleton around the ball is 1/2. Because I can take 1/2, mix it with 1/2, and so on. If you take, let's say, let's see if we can make it nicer, but we would have to go and look at the calculation. It would have even more.
I have it in my presentation. I can maybe share the screen and
Okay, sure.
Oh, wonderful.
somehow. Okay, can you see?
Yeah, perfect. Okay, so you see the drawing underneath are those survival function essentially, right? So you're basically taking a section. Let me just go there so I can hold. Like this is your linear functional, and so you're taking section and looking at sort of the parts of the ball that are above. And then you're trying to find essentially a point on, let's say, this upper part that mixed with A gives you O, such that you have, this part is the shortest, right? And so if you are here, you don't have any points. If you only have B, you have 1/2. Then as you go down, this increases until you get to this, to the equator. Then you would have 1, because now O is in the hull of that, so you can do everything, and then you go down and you keep having 1. Right, so you went. So if you're instead have the fraction capacity of A, then the set of A would be the only one that has 1. Everything else is 0, and the same thing for B. So if you are summing these two, right, you go from a measure that it's essentially only supported by the points, and it's one of the points, to a measure that does that, where you it's 1/2 at every point, and it increases as. And like one of the things that it's sort of interesting, difficult, is that if you take just two fraction capacity and you sum them, you do not necessarily have a fraction capacity. because there is no point such that the supreme of all of that. But the fraction capacity knows a lot about what things are orthogonal because it's linear when things are orthogonal. So there is some kind of notion of linearity hidden inside. And that's what you'd use in quantum mechanics. You would decompose on an orthogonal set. Then you know that you have a linear, an additive measure there, and then you make the computation of that. Yeah, so it's horribly complicated.
So the property that that will be a sum if the indicator are orthogonal. Is the point. If you are in quantum mechanics.
Yes, no, because then in classical mechanics, yes, but in quantum mechanics is because you're gonna have sets that are now in between the two, and you're gonna have interesting stuff going there because even there, right, A and B are orthogonal. You're summing them, and yes, the measure on A and measure of B where you didn't have support, it's exactly the linear combination of the two. And that is right. But all the other sets, now you have a much richer thing because now, like before you were on faces, now you become in the middle. Like it's you have the convex combination of the faces, and there is more interesting stuff going on there. And essentially, the way the things sum tell you about the convex structure, because it's based on the convex structure that you're going to know whatever things are possible. So in principle, there is a lot of information in this in this fraction capacity there.
Well, 15 now, if you wanna, which was when we planned to
Let's switch.
move on. Yes.
Thank you, Susanna. This was very interesting and helpful. Ready? Good to share.
Trying the right thing. Yes.
No, you're okay. It's just gonna. And can you also do the on the desktop? The webinar on the desktop.
Okay, so the quick.
There we go.
It's on the side panels and this work.
Okay, great.
Change it in the software.
Okay. So let me begin by trying to very briefly summarize what I want to do, and then I'll go into the details and make sure that I'll look at an easy description, but I want to make sure that you get the basics of what I want to talk about. So the starting point, I think, for what we want to do here is, first of all, we want to get away from probabilities and events. So there's this if you go back in the history of probability theory, there's some divergence, some parting of the ways, if you want. If you start with the first correspondence between Pascal and Fermat, you see that they have very different views of what probability is. And it is the Fermat view where you have a probability measure on a sample space that eventually won out. Whereas the Pascal view and later the Huygens view, which are that you have expectations and you don't necessarily have sample spaces, that one lost. Whereas we know now that this might have been different, and it could have been more useful to look at the other way. So in some ways, focusing on events and probabilities is like a red herring for some problems, especially in imprecise probabilities. So that's one thing I want to go to. Another objective is to unify classical and quantum probability, not necessarily classical physics and quantum physics, but we want to unify classical and quantum probability. And another thing is that we'd like to derive quantum probability, or Born's rule if you want. We want to derive it from the non-probabilistic axioms in a way, right? So make sure or try to find a way to get rid of the probabilities in a way. Yeah. And so I want to do this, and for this I will have to describe a very general framework, and I will make it as easy as possible. These are, for the first part of the talk, these are a few people who inspired me in this work. There will be other people mentioned later. I'm not going to mention them separately, but I wanted to mention them here. And the first part is actually based on this accept-reject formalism that was published in a paper some time ago. So what I will do now is, since we need to go away from events, and in a way we want to go from events to random variables. That's the idea. And so the basic idea to do that is we will look not at an algebra or a sigma algebra, we'll look at a linear space of random variables constants, right? But, and this will describe this accept and reject framework. And then I will apply what we've seen in the two cases, quantum and classical. So I'm going to talk about options, and options, you should imagine them as things that are uncertain rewards. So, and they live in the linear space. In other words, I have an uncertain reward, I can add them and I can multiply them with real numbers. Those are what I call options. Examples are, for instance, gambles or random variables. So I have some possibility space, and a function from possibility space to the real numbers is a random variable if you want. So these represent uncertain reward. Sometimes we have to talk about indifference classes of such gambles, so pull them together because we're indifferent between them. And then these are not gambles, but still we can consider them to be options that live in a linear space, just a quotient space. Or Hermitian operators on a complex Hilbert space could be also, so these constitute a real linear space, right? And we can also consider these to be options, because if I have a measurement, its outcome is uncertain, and therefore it could be considered as a random reward or an uncertain reward. So that is my option space. This is the very general way of dealing with it. How will I will now consider a subject, and a subject is uncertain about the outcome. It's uncertain about the reward that an option will actually give. And so we will look at a statement model, and a statement model is just a couple of two sets. A set A of the options that you, a subject, you, I will call the subject you. So the options that you accept, and this is operational in the sense that I'll ask you, here is an option, do you accept it or not, right? So this makes this operational. And then R is the set of all the options that you reject. I don't want them. Okay. The meaning, of course, then, if I have an option in A, this is an option that you want to get, right? If I have an option in R, you don't want to get that option. You don't want it. If I have an option in minus A, this means that you want to give away the option, right? And an option in minus R is something that you don't want to give away. Right, so this is the basic interpretation of what we're going to do. And because I'm in a linear space, this is all very, very standard. Okay. Other relevant option sets is, for instance, the intersection of A and R. So those are the options that at the same time you accept and reject. So this is what we call a conflicted option. This is definitely not something we want. And then here, if I take my linear space and I take all the options that I haven't said anything about, I haven't said I reject them, or I haven't said I accept them, I will call these options unresolved. Two more interesting ones. A intersection minus R is the options that I accept and don't want to give away. So these I find desirable. I want them, but I will never want to give them away once I have them. So these are desirable. And then A intersection minus A are the options that I'm indifferent to because I both want them and I want to give them away. I don't really care about them. Those are the indifferent options. Okay, so these are the basic interpretations. If I have sets of acceptable options, then I can define orderings on the space, vector orderings, in the sense that U will be at, well, this is a weak ordering. So if I want to get U in return for V, I will say that U is better than V, weakly better than V. This is strictly better than V. I want to get U in return from V, but I don't want the opposite operation. And this is an equivalence relation. This is U is equivalent to V if their difference is kind of different. So those are, what I want to say here is if I have sets A, T, and I, the indifferent ones, so the intersection of A and minus A, then I can also get to vector orderings. Okay, now this statement model, this set of acceptable and rejected options can be many things, but it can't be just anything. I'm going to impose a number of what we call rationality criteria. The first thing is obviously that you shouldn't be at the same time accepting and rejecting the same option. So the intersection between these two should be empty, which is fairly obvious, I think, as a rationality requirement. The second one is the most important one. And this is actually a reflection of the utility that you are attaching to these rewards. We're assuming that that utility is linear. Right, so this is a linear utility assumption, and the idea is that if I have a set of options, or if I have two options that you accept, then you should also accept any linear combination, positive linear combination of these options. So in other words, the acceptable options constitute a convex cone. So acceptability is closed under convex operations.
And cone also means that it's closed
Under
positive
all positive multiples. And this is because the utility is linear, right? That is the base. So this is the strong axiom. If you want probability theory, this is something that you should accept, because probability theory is based on this linearity assumption. Okay, and then well, another one which you can or not, or maybe don't want to accept, but this is typically what we do is you accept the status quo. So if you're extremely progressive, this is not something you will accept the status quo. But well, people who have a reasonable amount of conservatism will accept the status quo. Right. But this means that the status quo, so zero in this option means no change in capital, in a sense, right? So that is the status quo. And of course, since minus zero is equal to zero and both belong to A, with this means that you're also indifferent to the status quo, right? So this is why this axiom is called indifference to status quo. Okay, now given these, there's a lot you can do at this point. Notice I have not imposed, or almost not imposed, any axiom on the rejected options. The only axiom on the accepted options is the convex cone assumption. I haven't said anything about combinations of rejected options. But it turns out that we can say something about the rejected options by looking at the convex cone requirement, the conservative inference requirements, if you want, and the no confusion requirement. Suppose that I have an option that I haven't said anything about yet. So this is an unresolved option. And there are two possibilities for you to do, right? You can reject it or you can accept it. There's two things you can do. Rejecting it is always possible, but accepting it can become difficult. Because why? I already have my acceptable here. I'm adding the U, but then I also have to accept all the positive linear combinations of this. And it might be that by doing this, I'm hitting the reject set. Right. Because yeah, this is what something you specified. This is some set. This is another set. If I add U, and it might be that by doing this, even if the intersection of A and R is empty, by adding U, I could get to, because this is a generation axiom, this generates new acceptable sets, acceptable options, and so I could at some point intersect the R. That is the point.
POSI is the positive cone generated by that.
Yeah, sorry, I forgot. Yeah, so POSI is indeed the set of all the positive linear combinations, right? Yeah. Okay, so and in that case, I'm never able to accept U because it would lead to a conflict, and therefore I haven't done anything there. But the only reasonable thing to do is to reject it, right? So let's do that. Let's reject them because there's nothing else I can do. And then if you do that, then you get a number of axioms. These are the axioms at this point that I already have. So I shouldn't have a conflict. A should be a convex cone. And this is this requirement here that says that the idea, if you do the math, then this leads to this requirement. So
what is SH?
Sorry?
What is
this is the set of all, this is like the star. So this the positive multiples, the scalar hull is this. So it's the set of all the positive multiples of the elements of R.
Okay, so you're not taking the convex combination, you're just taking
I'm not going to take sums, I'm just going to take multiples. So if I do this and I subtract this is Minkowski subtraction. So any element in here and any element in here, if I subtract them, should still be in R. That is equivalent to always rejecting the sets for which this is mathematics. I'm not going to go into that.
Sorry, so R is not a cone?
R needn't be a cone at this point, not yet.
Okay.
Right. So this is the condition that we have here. A is a convex cone, and I have this condition, and then I accept the 0. I'm going to add one more thing, and that is I'm going to restrict the options that you reject to the ones that you're willing to give away. So I will only reject options, or will only reject options that you're willing to give away. So I'm going to assume, this is not necessary, but it makes the theory a bit more easy, that the set of rejected options is always a subset of minus the set of acceptable options. Right. Okay. Of course, in that case, the set of desirable options, which is by definition the set of all the acceptables and minus the R, will then become minus the set of the rejected options. So instead of specifying R in this case, I can equally well satisfy minus D, minus the desirables. And so what I have as a model that satisfies all these restrictions is a set of acceptable options and a set of desirable options, right? And the axioms are here. Okay, I can reformulate them as follows. So, and this is the summary. A couple M, A, so the acceptable minus desirable is what I call an accept desirability model if it satisfies these 4 requirements. So these are derived from the basic assumptions that we already have. First of all, 0 must be acceptable. 0 must never be desirable because you're not willing to give away 0, right? And then the set of desirables must be a subset of the set of the acceptables. So acceptability is weaker than desirability. They are both now convex cones under this restriction. They are both convex cones. And this is this is actually the no limbo requirement, or the requirement that we had on this slide. If we go back here, the no limbo requirement. This is this one. If I have something that is acceptable, and I add something that is desirable, the result will always be desirable. This is a very important requirement. So any couple, according to the rationality criteria that we imposed, any couple that satisfies these requirements will be called an accept desirability model. Now, if you look at these, and this is a very important point, if you look at these axioms, you can see that if I have that these are closed under arbitrary intersections. That is, if I have a collection of couples like this, and each of them satisfies these axioms, then their intersection, the pointwise intersection, will also satisfy that. And something that is closed under intersection always leads to conservative inference, right? For instance, topologies are closed under being a topology, closed under intersection. So you can look at the weakest topology that satisfies a number of requirements. Well, you can look at the smallest model that satisfies a number of requirements. So we have conservative inference. And in imprecise probabilities, this is very important, that you can do conservative inference based on a number of assessments. Okay. One more thing that I have to mention, and a crucial thing that I have to mention, is the notion of a background. So what do I call a background model? And I will denote this by, again, it's a couple, it's an accept desirability couple. So there should be a minus here, sorry. So it's a set of acceptable options and a set of rejected options or desirable options that you always accept, regardless of what you know, regardless of so they're always present. They're basic things that are always present. I will give you examples later on. Right? And in this sense, because they're always present, even if you know nothing, that's why I say that such a background model represents complete ignorance.
Complete ignorance in a specific context.
In a specific, well, you have a decision problem. You have options. There are certain options that you will always accept, and there are certain options that you will always reject, even if you know nothing at all. Right? That's what we call the background. That's a definition. Later on, I will derive backgrounds based on certain invariance principles. Right? That's the idea. So the V stands for vacuous. I have nothing. Good. Okay. And then, of course, I can combine this idea that there is this background with the previous axioms to say that I have an AD model, an accept desirability model, that respects a background if, where the first axiom, the axiom here, it's here, right? So the first axiom is that zero should be an A. I'm going to replace that with this axiom, which says that the background should be included in the model. So in other words, the acceptability background should be in the accepted set here, and the desirability background should be in the desirable set. And then again, zero should never be desirable. The desirables must be a subset of the acceptables. They're both convex cones and they satisfy the no limbo. Right, so the only thing I'm doing here is assuming that there's a background. And all the models should include this background. Right, so this is probability theory. Probably not the way you look at it, but this is probability theory. In order to show you that this is probability theory, I'm going to try and get to what you're familiar with. And in doing so, this is work that, again, is based on cooperation with and inspired by a number of people that you see. So in order to get to what I call Archimedean models, we need a number of extra assumptions. So I'm going to have, this option space was a linear space. I'm now going to provide it with a norm. So there's some norm. And this norm induces, so this becomes a norm linear space, and this norm induces a topology, a metric topology. I'll call the interior operator int and the closure operator. And then a functional will be, any real functional will be called bounder if its operator norm, which is defined in this way, is fine. So this is standard functional analysis. Right? I need one more thing, and that is what I call a unit element for this space. And a unit element is just an element, any element in the interior of the desirability background. So if this is this cone is the desirability background, I take the interior, so I take away the boundary, and I take any element in that interior. That is what I will take as unit elements. Okay, well, the question now is, are there other ways to characterize your preferences rather than this set A and this set R, the set of acceptable gambles and the set of rejectable gambles? Well, take any cone, any convex cone C, who and such that the unit is inside that cone. Well, I'm going to assume a bit more. I'm going to assume that this cone C includes the interior of the background, desirability background cone, and therefore the unit is also in there. Then I'm going to introduce two functionals. The first one is what we call the buying price functional. So it takes any option, any uncertain reward, and it associates a buying price with that. So what is it? The idea is I take the highest alpha for which I'm willing, suppose that this is the acceptability cone, I'm willing to get you in return for alpha times the unit. So this is like a price that I'm willing to pay to buy alpha, to buy the unit U. So this is the what I call the buying price function. And then the selling price function is the dual one. So I'm giving away U and I'm getting beta times the unit in return. And I'm looking at the infimum price for which I'm willing to do that. So this is an infimum selling price. I only need one of them because they are related by the conjugacy relationship, right? So the supremum, the selling price here is minus the buying price for minus the option. So I only need one of the two. All right. Well, here, if I have an option U, right? So what am I doing? I'm subtracting alpha times this unit. So I'm going in this way. I'm still inside here until I hit the boundary. And then this is the supremum alpha. If I'm outside, I'm going to have to go in the positive direction. So I'm going to have to add negative things until I hit the boundary. This figure already tells you that when I'm on the boundary, the buying price is 0. Right? I'm just hitting, I'm just going until the buying price is 0. Right? So the boundary is actually the place where the buying price is 0. That's a boundary of my cone. Okay? This already tells you that the cones that I have can, for instance, be closed here and open here. Right? I'm allowing for that. I'm not excluding that. But if I only look at these functionals, I'm not going to be able to distinguish between them because they're both 0 on the boundary. Okay. Well, there's a relationship. I can get to the convex cone starting from these functionals, but only up to the boundary. So the idea is that U will be in the interior of the cone if and only if the buying price is strictly positive, and U will be in the closure of the cone if and only if the buying price functional is non-negative. So this means that actually on the boundary, I will be able to use these functionals to characterize the cone. There's something else I had to say. There's a priori, there is nothing that guarantees that these values will be real. Just taking the supremum, it could be that this becomes infinite. Right? Why? Well, they are guaranteed to be real provided that this thing here is in the interior of V. Right? That is the mathematical condition. This is why I took the unit inside the interior of V. Right. So what am I now going to do? I'm going to take any model and I'm going to associate a buying price functional with it as the supreme acceptable buying price. But it turns out that this is equal to the supremum desirable buying price. And the reason for that is exactly the no limbo condition. Right, so these are, so whether I use the set of acceptable gambles or desirable gambles, they have the same buying price function. And the same for the selling price function.
Sorry, was that the condition where if you add A to D, you solve R in D?
The no limbo condition is the one where you have that A plus D is a subset.
That makes sense.
That makes sure that these two coincide. This means that I'm able to assign a buying price functional, not just with A and D, but with the entire model. So every statement model has a selling price functional and a buying price function. Okay. So now, if I know this, I will define a notion of a coherent lower expectation or a coherent lower prevision. A real functional from options to the reals is a coherent lower prevision if and only if there is some model for which it is the buying price function. Then I will call it coherent. I will call a model a coherent upper prevision if and only if there is some model for which it is the selling price function. And I will call something a coherent prevision or an expectation if there is some model for which it is both the selling and the buying price functional. So where buying price and selling price are the same, so for which this model is a fair price, because buying and selling have the same. So that is my definition of coherence. It's a bit annoying because in order to prove that something is coherent, I have to find a model and then do this. Turns out that there are independent characterizations of this So something is a coherent lower provision if and only if it satisfies these 5 properties. It should be super additive. It should be positively homogeneous. It should be continuous or bounded. It should be constant additive. In other words, if I add a constant times the unit, it's just like adding the constant itself. And it should be non-negative in the sense that if my U is in the desirability background cone, then its probability or its lower provision should be non-negative. So anything that satisfies these properties, there is a buying price. There is a model that such that the P is the buying price function for this. When is something a coherent provision? Well, if it is linear or additive, if it is bounded or continuous, if it is normalized in the sense that the provision of the unit is 1, and if it is non-negative. So here you see already the Finetti's definition of a linear provision on an arbitrary linear space is something that is linear or additive, continuous, normalized, and non-negative. This is the Finetti's definition.
Sure, for coherent provision, you needed it to be both the supremum and the infimum.
Yeah, so it should be a fair price. And so the thing is that this super linearity here, or the super additivity turns into.
Yeah, but this infimum and supremum, they were already always related by this kind of constancy, right? If you put the minus inside.
Yeah. So in other words, this means that this P lower here is equal to the P upper. Right, so I have defined the lambda defined with a model which is going to be this one, right? So the buying price functional is going to be this one here.
Yeah.
Right? And then I have the conjugate model, which is the selling price functional, which is the conjugate one, which is given by minus. So dot.
For a minute.
Yeah, this is the conjugate one. And then they're going to be equal to each other.
Okay, so is this a restriction on, like, before I think about putting a functional on top of it, is it a restriction on your AD model that these two things are the same?
Yeah.
So not all AD models
Not all
can have
AD
a
models will
coherent.
have this, right?
Okay.
Yeah. In fact, the ones that will have this, the set of desirable and acceptable functions will be semi-spaces, not just cones, but
Okay.
semi-spaces. And that you will have that for.
Okay.
So these are what we call the precise probabilities. These are the imprecise probabilities. So the precise probabilities is where you have buying price functional and
So your AD model already tells you whether you can have precise probabilities on them or not.
Yeah. Yes. Am I waiting for? I'm waiting for Gabriele, right?
I think he said to go ahead.
I could go ahead.
He said he'd be back in a minute.
Okay. So these are the they look a bit complicated, right? So I'm going to try and find an easier characterization. And the idea is that the vacuous model is also an AD model, right? So my background, the one that I had before, is also an AD model. It's the one that has the ID model for no information at all. So it also has a buying price functional and a selling price function. In other words, and I'm going to use that buying price functional and selling price functional to define what I will call an infimum operator on the linear space and a supremum operator on the linear space. Right, so these are very special, coherent upper and lower provisions. Right? I was just saying that I'm going to look for an easier characterization than this. Okay. And the idea is that the vacuous model, the background model, is also an AD model, is also an accept-reject model. And so I can associate a buying price functional and a selling price functional with that. I'm going to call the buying price functional the infimum operator on the linear space and the selling price functional the supremum operator on that space. Yeah. Okay, when you do that, this will again be a coherent lower provision and this will be a coherent upper provision. Well, there's a simple characterization. Something is a coherent lower provision if and only if it is super additive, positively homogeneous, and dominates the infimum. Something is a provision, coherent provision, if and only if it is additive and dominates the infimum. And this becomes interesting now. So these are the precise probability models on my linear space. These are the imprecise probability models. And their only requirement, let's look at the precise one, is that they should be linear and dominate the infimum. So this is where the background comes in. If I didn't have a background, anything linear would do. What restricts it, what is that it should dominate the background. In other words, this is the background information, the vacuous information, the thing that you always assume will be here. So provisions and probabilities, in that sense, are linear things that dominate the background. That is the idea. And the same then for the imprecise probability models, there should be superlinear. These two mean superlinearity and dominate the background. So coherence is linearity plus background. Keep that in mind, because it tells you that the background is extremely important. Okay, another thing is the lower envelope theorem. This is very, very basic in the sense that if I look at all the precise provisions, all the coherent provisions that dominate a lower provision on all options, then this is a convex closed set, and this P lower will then be the lower envelope of this. So this tells you, in a sense, that if you have a lower provision, it's an equivalent way of representing it is using a convex closed set of precise probabilities. Right. So any imprecise probability model can be seen as a convex closed set of precise probability models by the Hahn-Banach theorem. So that is another way of looking at that. Okay. So now you know about accept and reject. What I'm now going to do very briefly, how much time do I have left? About
Still 1:30, so 40 minutes.
oh, that's really cool. That's really cool. You can go as quickly as I
Including
can.
all our discussion.
I'm going to go slower.
Okay.
All right. I'm going to just first start apply this very abstract theory first to the classical case and then to the quantum case. So let's see if we can now do classical probability theory. The idea is in classical probability, so probability in classical physics, I have an experiment, right? And I don't know the outcome. It could be any of these, and this X could be finite or infinite. So I have here a number of possible outcomes for my experiment. And so the idea is that there's a variable. I don't know its value, but it could be any value inside this set X. That is the classical probability expands. And you don't know what the value is going to be. But you have preferences. So the idea is we're going to apply all that we've seen in the abstract case to this specific case. So the idea is my options are now going to be, as I said, they're going to be any map from the possibility space to the real numbers. And these represent an uncertain reward. So the idea is f of x, if I don't know x, I don't know f of x. So this is going to be a real reward that is going to be associated with x. For instance, if my option space here, or my possibility space rather, is AB, two possible outcomes, then any gamble is a point in this two-dimensional space, right? So this is the gamble f. It has coordinates f of A and f of B. So this is the reward that I get if A is the outcome, and this is the reward that I get if B is the outcome. So this is my option space. All these points in this two-dimensional space, or in general, any f from x to r is an option, is an uncertain reward. So I have a linear space of options because I can multiply these with real numbers and I can add them point-wise. Okay. What am I going to do? I'm going to assume that these functions are bounded. So I'm going to impose the suprema norm. You remember, I had to impose a norm. This is the norm that I'm going to impose the suprema norm. I also need a unit. And what better to choose for a unit than the reward that gives me 1 in every possible outcome. This is my unit. And it's in the interior well, I haven't said that yet, but I can associate well, no, I'm going to wait a bit.
So, so then you need the supremum to be well defined. So you couldn't have a gamble where your return keeps increasing.
If I'm on a finite space, there's no problem. If I'm on an infinite space, I'm going to assume that I only have bounded ones, or I could change my norm to include. But I'm just looking at this case here. Okay, so now what do I have? I have a unit, I have a topology, I have a linear space. The only thing I need is a background. So what is the background? What represents, in this case, complete ignorance? So I have a background model, and I will now denote that background model by ER. So A is the set of accepted options in the background, and R is the set of rejected options in the background. So if I know nothing, what options will I accept, and what options will I reject? Well, it turns out, and I will give you a short proof later on, but it turns out that based on a number of quite a number of independent ways of arguing, that you can show that this background should be between two boundaries. The first one is where my set of acceptable options is the set of all options that are for which there are non-negative everywhere. So if for two possible outcomes, it is this cone with the boundary included. So the positive orthant with the boundary included. This is the G greater than or equal to 0. And this one here, this is the one where I exclude the boundaries. So where the infimum value of the gamble is strictly greater than 0. And then this one here is the one with the boundary included, but not 0 included. That is this one. So it should be that there's no choice for the acceptable gambles. They should be this code. So the infimum, the smallest value, should be non-negative. And this here, there's a bit of choice for the desirable gambles. Either take everything excluded, all the boundaries excluded, or take the boundaries included, but not 0. Those are, and anything in between. If I take this as a background, and I look at the corresponding infimum operator for this background, it turns out that this is also the infimum of this gamble, right? So the smallest value of the gamble, which is why I call this the infimum operator. But for this background, the infimum operator is actually the smallest value of the gamble.
So how do you get that that's your background model?
I will try to explain it. Right. So again, remember, A was so assume I know nothing, right? Or you know nothing. And A is your accepted gambles, R is your rejected gambles, D is A intersection minus R, and your indifferent gambles is A intersection minus A. There is no confusion, and there is 0 is accepted, and R should be a subset of minus A. So this is what we have in our heads already. Okay, first argument. If I have a constant mu that is non-negative, then if I turn that as this constant reward cannot give me anything, I cannot lose, right? Because I always get a positive amount or a non-negative amount. So I should accept that. This is a very weak requirement. You should accept anything that you can't lose money from or utility from, right? Moreover, there's a monotonicity argument. Suppose that the smallest, if I have a gamble and the smallest value is dominated by such a non-negative mu, in other words, then I should also accept it, right? Because it's higher than something that I will accept anyway, and that I can't lose from. This tells me that if the infimum of a gamble is greater than 0, so the smallest value is greater than 0, I should accept it. Same argument now for reject. Suppose that I have a negative constant, then the constant reward that is associated with it, I can only lose constant amount of mu, whatever. So I can't accept this. I should always reject this. Very simple argument. If I have something for which the highest value is smaller than such a negative mu, then I should also reject it. In other words, anything that has a supremum or a maximum, if you want, that is strictly negative, should be rejected. Because of this, I already have lower bounds on the set of accepted gambles and a set of rejected gambles. First of all the gambles that are non-negative, the ones here, should be accepted, definitely, and all the ones in here should be rejected. So I already have lower bounds. The thing is now, how do we get to higher bounds? In other words, how can I bound them from above? There are many ways to do this. One way could be, and this I think is a very weak way, but I'm going to tell you anyway. I'm going to just, because adding gambles to a set A means becoming more determined, right? Becoming less conservative. So I want to be as conservative as possible, and therefore I will let my A be equal to the smallest bound. And the same here, same for rejected, right? I find this a weak argument. There are better arguments than that. There's the one with complete ignorance. The idea is that my set A, my set of acceptable gambles, should not change under the transformations that are typical for classical physics. And that is, in classical physics, what can I do? I can permute the axes. I can, because my part of classical physics, if you have the outcome of an experiment, and I can read it. So for instance, heads and tails, if I do a heads and tails experiment, what are the transformations of the linear space that are allowed in classical physics? Well, I can rename these, right? I can permute these, and that's about it. I cannot rotate this. I can only permute this. And then I can also lump certain things together. For instance, I'm only interested if there would be a third possibility, like on the side, right? Then I could say either it's on the side or it's not on the side, and then I'm going to lump head and tails together, and that is also a reasonable way of doing a transformation.
And your weakest background had like the boundary included, right?
That's already there.
The other one had like them not included.
Yeah.
And I guess you could have some in between where some boundaries are included and some are not.
Yeah.
But here,
But nothing else. Yeah, but that precludes that there is anything.
I treat them all the same.
Right. Yeah,
Okay.
It's a very simple idea. So you can prove that this kind of invariance under all these principles is actually equivalent to this principle that says that if I have a gamble that's acceptable and another gamble G such that the set of values of this is included in F, then, so in other words, the values of G are included in the set of values of F, then you should also accept. That is equivalent to this symmetry principle. And then we're done, right? Because so assume that a gamble is acceptable. Because of this principle, yeah, I can, this will mean that if I take a gamble that is constant and in there, in other words, f of x for some x in x, and I make it constant, so I take f of x, which means that this gamble here is constant, and its value is included in f of x, and therefore this should also be an A. Right? You see the argument? Very simple one, right? So I take a very special G, namely the constant G that takes the value f of x for any x in A. And since this is satisfied, this means that this constant should also be an A. Right? So this means that this should never, because it's acceptable, no confusion tells me that it should never be rejected. Right? But a constant should not be rejected if and only if, and this is the first equation that we had here, this one. It means that this f should be non-negative for all x, because if f were negative, I must reject it. Right? So the idea is, suppose that this were negative for some x. If it's negative, I must reject it, but I can't reject it. Right? So this must mean that this is positive of non-additive, which means that the infimum should be greater than 0. So this tells me that A should be included in the set of all the gambles that are non-negative. So I know, or I already know that this set should be included in A, and now I've proved that because of the symmetry, I think I've shown that A is also included in that set. In other words, A is equal to that set. And a similar argument, I'm not going to go through it, for the rejected sets, which tells me that the rejected sets should be, or the desirable sets, if you want, should be in here. So it should be between the infimum greater than 0 and the infimum greater than or equal to 0. So this is just the symmetry argument in classical physics that tells me that the only thing I can reasonably do with my gambles is I can never take convex combinations of the, I mean, I cannot rotate my frame of reference. I can only permute the axes. Okay. So that's it. Now, remember, precise probability was two things, the background and additivity. So now I know what the background is in classical probability. So now I can look at what are the precise probabilities in classical probability. So they must be linear. So let's look at the case of a finite thing. This is, I just expand f in the standard basis. So this is the unit vector in the x direction. F is just this linear combination of these unit vectors. Linearity tells me that the provision of f should then be the sum of f of x times the provision of this thing, which I will call p of x. So it's the inner product of p and f, where p is some real valued function. Right. This is linearity. Now I'm going to use the background condition that says that p should dominate the infimum. And if you do that, as a result of that, you find that the sum of the p should be 1 and p should be non-negative. This is, in other words, this tells me that this p in the classical case must be the expectation associated with some probability, mass function. From two principles, the background and linearity. So this tells me that something is coherent provision if and only if it is the expectation operator associated with a probability in the finite case. That's one thing. So right, so I think it's important that you see that it's only linearity and the background that we deduced from symmetry principles. Quantum now. And this is work, well, Alessio is here. So this is work based on ideas by Alessio, Alessandro, and Marco Tapalon. And it's also work that we at some point worked on, and that I base the similar argument that I'm going to do here. So the idea is you have a quantum system, the state is unknown. You don't know psi, the state. And because in a time-honored tradition, I'm going to denote this by a capital psi because capital means I don't know it. So this psi is an element of the state space, the Hilbert, complex Hilbert state space. I'm going to assume in this case finite dimensional. And it's normalized. Now, what are the options? What are the uncertain rewards? In this case, I'm going to take the measurements as uncertain rewards. So all the Hermitian operators are measurements in this finite dimensional case. And I'm going to, the idea is that if I do a measurement on a system in an uncertain state, the outcome will also be uncertain. Right? And the idea is that the outcome of the measurement is the reward that I'm actually going to get. So I'm going to, you have some idea about what state the quantum system is, and then I'm going to ask you, do you accept this measurement, knowing that you will get as a reward the measurement itself? Right? So again, I have a linear space of operators, in this case, n squared dimensional, real space. Right? I can have an inner product and a norm. So I will take the Frobenius norm. Doesn't really matter in this finite dimensional case which norm I take. They're all equivalent. And I will again take a unit. And what better unit to take than the unit measurement, which gives you 1 whatever happens. So I will take this. Again, the background model. What is the background model here in the quantum context? Again, it represents complete ignorance. So the same argument, using the symmetries that are allowable in quantum physics, because all the unitary transformations of state space leads to the conclusion that under complete ignorance, my state must be all the non-negative definite, or the positive semi-definite rather, positive semi-definite operators, and the desirable ones should be between all the positive definite operators and the operators that are positive semi-definite and non-zero.
You don't need to be unitary, no, it's just,
Sorry?
you don't need to be unitary, just PSD, no, the unitary.
Yeah, you can do more than that. Yeah.
What is PSD?
Positive semi-definite, so the emission operator that are positive, with a positive, non-negative eigenvalues.
Okay, so you're basically just increasing the norm and that's it.
So you know, you need the unitary to preserve the density operator, no, and the metrics.
Yeah.
But the transformation that, so you need the transformation that are invariant for the positive code.
Yeah.
It's a bit, so they don't need to be unitary, they don't need, you know, the eigenvalues to sum to one. Yeah.
Yeah, that's what I'm saying, like you're just going,
Yes,
increasing the norm.
Yeah, they're the scaling.
Like
basically.
you're scaling everything in the same way.
Yeah, but I'm not, I only, doing this is enough, right? Because if you have this as a background, then it will work, but not necessarily. I'm doing the argument in the other way around. I'm deducing this from the symmetries. Right, so if I have this, and of course it will satisfy what you're saying, but I need to deduce this from in the same way that I did it in classical physics. So what are the transformations that are allowed? There's the unitary and perhaps also collapsing certain directions in space. That is what is allowed. Again, the idea is, I'm not going to prove this here. It's a very similar argument. And this implies if you have this, then the infimum operator that is associated with the measurement is just the minimum of the spectrum, so the smallest eigenvalue. That is the infimum operator on this option space. Very simple, very easy. So this is the price, the supremum buying price associated with this set of.
Does it work also if you have a continuum spectra, or?
Then you will probably have the infimum here, right? I think you can repeat the argument. You will have the infimum.
Yeah, but you don't need the eigen states to exist.
You need it to exist, yeah, probably.
Then it doesn't work.
Yeah, probably. So this is why at this point, this is what I'm going to say later on. I need to extend this to the infinite case and to other contexts, right? So if you have this.
Sorry, could you also just say again, you have the positive semi-definite, positive definite in the middle with the.
So these are the positive definite ones. This is the minimum is greater than 0, and this is the minimum. There's the eigenvalues can be 0, but not all of them.
Okay.
Right. So the eigenvalues can't be 0, but as soon as one of them is strictly greater than 0, then so this is what the same as the case where you had all. So the boundary is included, but not this one. Yeah, that's the idea.
So do you strictly need the collapsing of direction, or the permutations are?
But there are other ways of getting there as well. But collapsing is. I'm not sure that unitary is enough.
You're not sure.
I'm not sure. I think you need probably. It's not enough in the classical case. Permutations are not enough. You need to be able to take things together.
What is it that doesn't?
But there are other principles that get you to the same point. But I can talk about that later.
Yeah, because just to give you a sense.
Yeah.
Permutations are exactly a transformation for which the entropy is invariant.
Yeah.
And all the unitaries are exactly a transformation for which the entropy is invariant. So if we can get to that, that would answer the question that I had.
That would answer the question. Well, we can come back to that later because there is some point of that I haven't proved that out yet. So, but if you take
the continuum, you might actually be able to use continuity because I don't know that you're using it.
Yeah. Okay. Well, okay. So now again, what are the coherent provisions in this case? They are linear, and they must dominate the background. what is the background? The background is this minimum operator. So, well, by linearity and the Riesz representation theorem, I know that for any provision, since it's linear, it's a linear functional on the measurements. So there must be some measurement such that this is the inner product of the two. This is the Riesz representation theorem. So there must be some BEP, which is also a measurement, such that this P of A is the trace. So this holds for bilinearity. So the only thing that I have to impose extra is that this P should dominate the background. But if B dominate the background, this just amounts to BP being a positive semi-definite with trace 1. So this becomes a density operator. In other words, P is a linear provision, additive, and dominates the background if and only if it satisfies Born's rule. So the only thing that we had to do to derive Born's rule is assuming linearity and the right background. And the background follows from invariance principles. So the point is, if I have a linear space that is n square dimensional, it could be a classical experiment or it could be a quantum experiment. As far as I know, it represents a linear space. Since it's n square dimensional, it could be a quantum experiment in an n-dimensional Hilbert space, or it could be a classical experiment in the classical case. There's a priori nothing to distinguish between. The only thing that distinguishes between the two are the symmetries that I can impose that are natural for a quantum experiment and for a classical experiment. And as soon as I do that, as soon as I impose the symmetries, I immediately get to either quantum probability or classical probability. Right? So that's the idea. Yeah.
Yes, just a question about the lumping. But do you need it because you are considering composition of experiment? Like, for example, if you have two coins, is that where you need the lumping, or because you have in principle you can have two cones, no, two positive cones for cone 1 and cone 2.
Yeah.
So why do you need this lumping in the?
It makes it easy. I haven't found a way at this point. I haven't found a way to do without them. But there's this lurking suspicion that I might be able not to need it.
But so if you, for instance, if you work like with the coin, only with the coin, you don't need that, no?
No, yeah, then you don't need it.
Or with the, let's say, one particle in quantum mechanics, even if it's n-dimensional. So you only need when you have two objects.
Yeah. Yeah. So, well, okay. So this brings me to the end, I think. First of all, a few important takeaways. I think probability theory in the form of AD models is just, it comes with conservative inference, with a deductive inference system. And so it allows us to specify probabilities only partially. That is one. The second important takeaway is that precise probability is just linearity plus background. And I think this is a very important message, right? Background is crucially important. And the difference between classical and quantum probability is only in the background. And you can derive that background by looking at symmetry. And so the connection between classical and quantum probability, it kind of stares you in the face as soon as you have the right language. Well, and then another idea is that if you work with, so remember, for imprecise probability models, you can work with a set of options, a set of desirable or acceptable options here. And options are measurements, so you can work with sets of measurements. And that would be the Heisenberg picture of quantum mechanics. Or you could work with sets of provisions, which turn out to be, in that case, sense of density operators or sets of mixed state, and that would bring you to the Schrödinger picture, which again, on this approach, are more or less equivalent to each other. So you have both a Heisenberg and Schrödinger picture on this account as well, if you wanted that. So that, I think, summarizes what I wanted to say.
So how do we impose the invariance under unitary transformation? You really need to know that you have some type of Hilbert space structure underneath.
Yes. Okay, indeed, yes. So what would I like to, how would I like to extend this? Because this is something that is known now. How would I like to extend it? Yeah, because I forgot to say that. So first of all, I would like to go to infinite dimensions and see if we can easily extend it there, these ideas. And then we can in the classical case, it's not a problem. And then the other case is all of this assumes the underlying Hilbert space structure, right? And so the question would be, can we do without this? And that is something that I don't know at this point. I'm very interested in trying to do away with all that and still get to the same results, not needing to assume the existence of probabilities, deriving it from other things. Right.
Right. So the way that I'm trying to think it, how it intersects with the ensemble space. So you are not starting with the ensemble, you're starting just with the space of linear functional. Right. So you basically say, I have all these linear functionals. And so again, for the topology, in quantum mechanics, there is this problem that Hilbert spaces don't quite work because they assume states that do not make sense. And the operators, even operators like position and momentums, are not continuous. Therefore, you can have a sequence of states that converge to a state, but the expectation does not converge to the expectation, right? This is a complete nonsense physics. One of the things that we are trying to understand is what space we should use. And if we just have position and momentum, it's safe to say that the Schwartz space is the correct one.
Yeah.
And the Schwartz space is nice. It is locally convex topology vector space, but it does not, it's not a Banach space. It doesn't have a norm. Like it is locally convex. You have accountably many semi-norms, and you can define a distance function out of that. So it's a metric space, but it's not a norm space. So when you were saying, oh, I have a norm, I'm going to have spaces where I don't have norms. And if we need to put the right topology on function spaces for field theory, I suspect that this is going to be the similar situation. I hope we're going to have locally convex metrizable space, which means you have the semi-norms, but you're not going to have a single norm. So that's one thing. And so, okay, so you have essentially a space of linear or affine functions. You have that, and you kind of want to be able to define the state space based on that. That's essentially what you're trying to do. And we want to do it in a general way in the sense that okay, so we basically say we have these things, and then we have a bunch of symmetries defined on this, which are most likely going to be the Lie algebra that we've been talking about. And so that's gonna tell you how things change with respect to the others and all that. And now we have the problem that okay, you need to distinguish between classical and quantum, and if we just give the first order of the algebra, you're not gonna be able to do that. But if you get all the completely algebra, then you would know, because as Marcel was saying, the second order operators are gonna be different, but I have no idea how you would be able to use that. But in principle, you should be able to use that to then say, oh, okay, the background between classical and quantum are different because yes, first order is the same, but second order is different. And then in principle, by the symmetries, you should be able to get what you want without even, I have no idea how to do it. But at least I see that the ingredients are there. Okay, because you want to start with the functionals, have some type of symmetry on top. And the other ingredients, so the topology you get, because the topology you basically say, I have not just a linear function, they're gonna be the continuous one, and they're gonna separate the points, and so the topology is the one generated by that. At that point, I think it's more direct than saying that I have a norm. I have the continuous linear function, they generate the topology. You're gonna be locally convex because you can say there is a continuous countable family that it's enough. And then you get then the other thing that I don't see how that you need to get, I don't know how you get, is the entropy itself. And this is what I was saying before, is whether, and I don't know if it works, whether the the space of the symmetries is one-to-one with the entropy. So once you know the entropy, you know the space of the symmetry.
Yeah.
Right, that I don't know. It might be because the Lie algebra might have even more information. So it might be that you're looking for a functional for the entropy that has some specific. I don't know what are the requirements in terms of the observables, but there should be a way to translate all this thing. And then you would be able to say, okay, for this space, given the symmetries, I'm gonna have my entropy defined in this way because it has to be invariant for that. So that there should be enough pieces. I just don't know how they all fit together.
Yeah,
But it's basically the inverse problem of what we're doing, right? And then you also have the issue, well, but that's a simple issue, right? Because probability theory, as we were saying, is going to be greater than physics. And so the idea there is that you're going to have symmetries that are not going to be Lie algebras and all that. So that should cover the case that you have a probability theory and it's not mechanics, it's not a physical theory, but you can still do it. And so, for example, in a classical continuous, let's say that you just have one variable, right? You probably still have a symmetry of translation and invariance because you don't know anything. So your symmetry is translation and invariance, which is a kind of permutation. But since you have continuity, I don't know that you can, move things around. So I don't know if it's enough. But that would have something where the entropy is not uniquely defined because you don't know the Lebesgue measure. Sorry, I was ranting a little bit, but I think that there are a lot of pieces. Yeah.
There's one more thing I wanted to say, and this is also for the sake of Alessio, because I think at some point you published a paper where the paper on exchangeability. So the idea here, so the importance of this background, I think, is also there. So even in the case of classical probability, for certain problems, you can use a different background. If you have repeated experiments that you consider to be exchangeable, this infimum operator will be not necessarily be the minimum operator. It will be another operator, typically, and then you have additivity with respect to a different background, which will give you how shall I say? You will have an expectation operator, but with respect to something that is not a probability measure, right? But something else, and this is equivalent to this. So you will have a type of integration, but respect to something that is not a probability measure. It will typically be a signed measure if you want, but this is also compatible with this law, right? So this background is very important. So the idea is this is something that is linear, but then the background determines what type of integral. If you want to talk about measures, you don't have to because you do everything in the language of expectations. But if you want to talk about measures, then this will tell you what the type of measure is that you can achieve. And this is a very nice contribution, I think, that you did in the paper on exchangeability.
Yeah, you have actually a slide later about this. Yeah, just we take the measure relative to that linear operator. Yeah.
That is then the connection between non-additive, but with expectations that are not just, or with P that are not just expectations with respect to probabilities. Yes.
Yeah, thinking on how to connect this with what I know. So are these U's and V's, for example, are those density operators, or are these almost like Hermitian matrices?
Sorry,
Like this P turns out to be the expectation.
in the classical case.
The expectation needs a state and an observable, right? I like usually I would ask what do I expect for the position given that I am in this state, right? I would need a probability measure and I need my random variable.
These are
How
expectations. In the quantum case, just let me
Yeah.
specify. In the quantum case, you have expectations on measurements, right? So you have functionals on measurements, not on the state. Right? My functional is on the set of all measurements. It's the measurements that are the variables. Well, you could do a measurement of a state of a projection on a state, right? And that could give you the probability of the state, if you will. So if you have a projection operator on the state that is 0 outside and 1 on the space, then you could define the probability of the state to be the expectation of that function, right? So then in that sense, you could also get to probabilities on the states. Yeah. Okay, sorry, just wanted to
yeah.
sure.
Sure, like I can start with expectations and then recover probabilities as expectations of like projectors.
No, sure. Well, with the trace operator, right?
Yeah.
Yeah.
So yeah, I mean like if I want to know the probability, like in classical probability, would just like if you want the probability, calculate the expectation over indicator function. So I get that. I don't need to talk about probabilities directly. I can talk about expectations. That's fine. Still, I'm wondering if the U is a Hermitian matrix or specifically a density matrix.
Well, what's the U? Yeah.
Is the U in the
U is
input to your function?
Is a Hermitian matrix.
You know, is an observable.
It's an observable.
What?
Yeah.
How? What? I need to know the state that I'm in to say what the expectation value of that.
P is like
Yeah.
P
The
is
P-
the trace. The P is the trace and the row. Okay, together.
It's together, so the state is encoded in the function itself, P.
Yeah.
Good, okay.
The trace give you the linearity, and the row gives
yeah,
you the
I see,
the meat of the.
For every state, there will be a different P.
So it's the usual dual of a dual type thing, right?
Okay, yeah, it's baked in. There's no one P, there are many P's for every state. There's one. Okay, I get it.
And then this imprecise one, because this corresponds to a set of probabilities, this will correspond to a convex set of let's say it's just, yeah. Okay.
1:30 here. Well, maybe we should take a minute and check with Susanna and myself so we have an hour and 15 minutes scheduled lunch break here now, and then I realize it's already evening for you in Europe. So I don't know if you're planning to join for any of the afternoon. These are you'll be able to see the recording, the video on YouTube if that's helpful. And you have time and inclination tomorrow morning your time. Are you planning to connect at all tomorrow morning our time?
So I will not be able to join in the afternoon today, but
Right.
I will connect at 9 in the morning your time and join the meeting again.
Okay.
Yeah,
So
the same for me.
I think the schedule is 9 o'clock, right?
Yeah, yes, it's 9 o'clock again. Okay, so then if we have at the end of today, this afternoon our time, we'll discuss topics to be discussed further tomorrow. And then we'll certainly plan ones that involve you guys.
Well,
for the morning, and we
if
should
you have
email-
suggestions, exactly.
No, yeah, if you have suggestions of what you'd like to discuss tomorrow, please email Gabriele and me. And then we will, based on what we discuss at the end of this afternoon, we will email you. So you have an idea of what the plan is for this, what the focus will be for discussions tomorrow morning, and for anything that we think would particularly involve you, we'll make sure to schedule it tomorrow morning.
Okay, that sounds good.
Okay, thank you so much for joining and presenting remotely. We're sorry you couldn't join us here in person in Michigan, perhaps in the future at some point. And we will be in touch via email later today and talk to you tomorrow.
Okay.
And
Thank you.
anybody also who is following on YouTube, we are gonna probably interrupt here, and then I'll create a new stream later because I can't pause the stream anyway. I don't think it makes sense to just leave it on. And also hi to Alex Wills that I see you now on the attendees. Okay, so we'll stop here and we'll reconvene in an hour.
Well, 1 hour at
Uh-huh.
2:45,
2:45.
1 hour, 13 minutes.
1 hour, 13 minutes. Okay. Stream.